there is a relationship between temperature and the evaporation and the transport. So, but that's just one piece of evidence. So that's this modeling, right? So we use hydrosphere to model vapor transport. It's one of the few models actually can specifically have the vapor component. Most of hydrological models we talk about water. This one is a more component. Yesterday, some people asked me how data you can actually be like a trust your model, right? So this is a good example, right? We are working in a very remote area. We don't really have much data at all, right? So the only data we have is the temperature data and the soil moisture data. So we basically that's the only thing we can actually validate the data, the model at, right? So for example, on the left, that is temperature data between observation and the modeling, and on the right is the soil moisture data between observation and modeling, right? So for temperature, we spot on. It's very easy to model temperature, right? So, but for moisture, we are okay, at least from the kind of from the mean value, the observation and the simulated value, they are very close, right? So, that's it's not perfect. It's not like we can validate every parameter, right? But at least we validate what we have, and is actually reasonable. And then we can then use that model to simulate the vapor flux, and that is actually vapor flux from a gravel plain from a sand dune, right? So you can see it's actually above 0. That means they do have positive flux into the atmosphere, right? So that's basically give us the kind of a mechanic-based evidence to show, okay, there is a possible groundwater can transport vapor all the way to the atmosphere, right? So give us evidence to say that. So, but again, yeah, that just give you an example, how much data you need to validate your model. It's really based on your question, right? So, for us, we propose a new hypothesis, and we are working on a region without much data. People are okay with that, right? So it's still publishable. So that is transport, the mechanism part. So the next part is basically reverse. So we know the groundwater can impact soil, can impact fog formation. But how about like fog impact on soil moisture? Right? So because we know soil moisture is most important parameters we think about in terms of vegetation dynamics, right? So, that's vegetation need soil water to grow, right? So soil water really has impact on wildfire, on the meteorology conditions. Like for example, when we think about the thunderstorm here, that's very closely related to soil moisture level, right? So also soil moisture is responsible for like soil biochemical process, and is also responsible for like vegetation patterns. In dryland, in the last slides, I will show you a vegetation pattern, how that linked to soil moisture. Right? So basically just tell us, soil moisture is a very important component of a dryland ecosystem. So that's why we try to have a good understanding how do we, and how fog actually impact soil moisture. So again, we did kind of two ways. So we first did observation, and then we develop a model and try to simulate that. So this is first is observation, right? So there are 3 locations: gravel plain, sand dune, and different type of gravel plain. So on the top, they are the fog events, and this line is the soil moisture dynamics. So what we saw here, that's the mean value variation and the fog events. But basically what we saw here, that is during the period there's no rainfall events. Like I mentioned, rainfall events is very rare in this desert. Sometimes, maybe only once per year. Sometimes there is no single rainfall events the whole year. So but we do have a frequent fog here. And you can actually say, right, after fog events, some actually did start having small peaks. So that's already tell us, fog does play a role in terms of driving the soil moisture dynamics. So then, next step as a hydrologist, you want to be able to simulate that, and then you can do future prediction, right? So that's the goal. So, but there's nobody actually has been incorporate fog into soil moisture model, right? So you have to do that on your own. So what we did is we first try to look at the fog distribution, right? So and then see whether we can, because if the distribution is similar to rainfall, we can then think about we incorporate the process into existing model using the principle of rainfall, right? So that's the idea. So when we plot the fog distribution, we found is actually fit well with a Poisson distribution. So that's actually for rainfall actually also follow a Poisson distribution. So the unique thing for Poisson distribution is you can compose the time series into two components. One is basically the average rate, like how much fog you have, the frequency of the fog, and also the how much per fog events. Similar to rainfall, you can decompose to like how big per rainfall events, and also how often rainfall happens, right? So that's a good thing. So fog actually follows the same statistical distribution as rainfall, and because of that, we were able to then modify stochastic modeling framework. So that's developed from my advisor's advisor in Princeton University. So the idea is, this is soil moisture dynamics. DS is soil moisture, and then you have the root zone, like a depth, how deep the soil is, and then you have a porosity, right? Basically the property of a soil. And then there are three loss functions. Right? This one is through evaporation, this is transpiration, so that's a leaching loss. In dryland, a lot of time leaching loss is considered zero, right? It's very small. And for evaporation, you basically, based on soil moisture threshold, you model evaporation. Sorry. So really, the unique thing, what we did here is we add fog into this modeling framework, right? So because fog is different from precipitation, right? For precipitation, you can use rain gauge to measure it, 1 milliliter, 2 milliliter, right? So that is a fixed unit. But for fog, when you use a fog collector, it's actually horizontally, right? So you have to do some correction. So that's why we introduced this one as a kind of a conversion factor from horizontal water to vertical water. Right? So after we modify this framework, we can then simulate fog impact on soil moisture. Right? So we can provide fog input and then see how well we can actually simulate soil moisture. So this is results between observation and the black line is observation. So the pink line is a simulated one, the modeled one, right? So, of course, they are not perfect, but it actually captures the major peaks, right? So that's already a big advance, right? So, like I mentioned, in the past, nobody were able to model fog impact on soil moisture, right? so far we look at soil moisture, right? So, but when you think about plant water use perspective, it's not soil moisture actually play, it's actually soil water potential, because water flows through potential gradient, pressure gradient. It doesn't matter what soil moisture you have. So that's why we also look at the fog impact on soil water potential. So we use a device called WPT4. I don't know anyone heard of this, right? So it's basically a device you can put a small amount of soil sample in there. It actually will take a reading of the soil water potential of that sample, right? So give you the idea how dry or how wet the soil is. So, and then what we did is in the field campaign, what we did is we'll collect soil sample from different habitats, some in open area, some in the riparian area, some under the vegetation. So we can look at what's the soil potential before the fog events, and then the blue ones are after fog events. Right? So we can say basically regardless where we are, right? So you either open space or under some vegetation, after fog events or dew events, you can say actually there is a big increase in soil water potential, right? So very large increase. So regardless which year, right? So that's already tell us, fog actually did play a pretty important role in soil water status, right? Actually increase soil water potential dramatically. So that's the first step, right? So look at the soil water potential. And then the next step will be how really fog impact vegetation water use, right? So how do we do that, right? So we basically look at the similar idea, but we look at the soil, plant water potential. So what we did is we use a device called a pressure bomb. So it's a scary name. But the idea is pretty straightforward. You put the plants into this opening, and there is a pressure we add to squeeze the plants until water coming out. So that under that pressure, that is a plant water potential. Right? So you typically do that before sunrise. So it's called pre-dawn water potential. So that's because at that time there's no transpiration yet. So the plant water potential should equilibrium with the soil water potential. That will be the time, the maximum water potential plants have during the day. Excuse me. So basically what we did is we'll get up very early in the morning before sunrise. We'll go to the site, we'll cut the small twigs, and then we'll put them into this device, and we'll measure the pressure from the plants. And then we'll do that during normal days, right? Then we'll do that during fog days. After fog events, we'll go there again and measure it. So we did that for like almost all the major species from that region. So, and you can see basically the vast majority of the species, only I think one species, Calicarama, so only this one didn't really show like much response. But for others, it's really like a big difference between fog and ambient condition. Right? So basically, after fog events, the plant water potential dramatically increase. Right? So that's basically telling us that plants actually can directly benefit from fog events. So remember that's a twig, that's a branch. Right? So after fog events, their branch water potential increase dramatically. Right? So that means they are directly benefited from the fog water. Right? So that's a morning fog, but it's very interesting. Like if most of the fog events in this region coming from the morning hours, but there's some fog events come at night, like 9 p.m., 10 p.m. So it's very interesting for this type of night fog. In the morning when we measure water potential, plants really don't benefit from them. So it's very interesting. Like only morning fog actually benefit plant water potential. Night fog it doesn't. So we did the same thing for dew events. So basically, if you have after we have a dew events, we also go out and we measure water potential. We compare that with condition without dew. So you can say, for regular dew, there are only maybe 1 or 2 species show response. Majority of them actually didn't really show response. But when we have a heavy dew events, so what we saw is actually most of the plants then start showing response, right? So to me, that's really basically telling us that dew is relatively small events, so plants won't be able to take advantage of that if the water amount is so small. But if you have a heavy dew events, that's almost like a fog now. So plants can then start taking advantage of the additional water they have. So then the next thing is some plants, almost all the soil samples, right? So they show response to fog events, but not all the plants show response. So when we did a correlation between soil water potential and plant water potential, you can see most of the species, they are significant But there are two species, they are not significant. Their correlation are not significant. So, but these two plants did actually show the response to fog water. So that's telling us, very likely these two plants at least, they actually taking up the water from their foliar uptake, from their leaves, not from the soil. Right? So for others, very likely they benefit the fog water through the soil water. Right? So, but for these two species, very likely they just directly take up the fog water or dew water into their tissues. Right? So that's just give us some indication how they use this water. Right? So, but that's a correlation. Right? So it's not the most direct evidence, but point out to that direction. So far what I talked about here is mostly based on the ground observations. Right? So it's based on there are limitations. We only go there maybe a certain time per year, right? So only certain days. So how do you do that? From a more continuous level, right? So that's why. Also, we did find the impact so big that make us try to think, move even further. Whether we can use remote sensing to actually do that, right? So that's our next step. We want to say, if the impact of fog on vegetation is so big, whether we can see that from space. So that's what we try next. We're basically using remote sensing to look at whether fog has impact on plant greenness. So we choose two sites for the remote sensing application because that's the part you have the dry rivers. So there are more vegetation because a lot of the sites, if the vegetation is so sparse, remote sensing won't be able to tell from vegetation on the background. Right? So the index will be very noisy. So we choose these two sites. One is the Goldberg pipe side, one is called the marble copy is here. Right? So what we did here is that is a time series of at the bottom is all the fog events, and then on the top that is the EVI value. EVI basically is the enhanced vegetation index, right? So in a nutshell, that's basically give you the greenness of that region, tell you how much plants are there, right? So that's EVI. So we use EVI, we use VOD, right? So that's an optical vegetation optical depth. So this one is just different wavelengths. Right? So this is more like a microwave wavelength, and this is more from the regular wavelengths. You can see. So, but anyway, so we use a different indication of vegetation growth. So what we saw here, you can see there are already some indication when you have fog events. The vegetation index starting bigger. Right? So that's already gave us some indication. And then building on this, we can run some statistics. Right? So for example, we can on the x-axis is the fog amount. So that is a ground-based measurement fog amount. But y-axis is the NDVI or EVI or VOD. They are all indicator of vegetation growth. So you can see actually there is pretty nice. Pretty nice means is a statistically significant relationship here, right? So they're noisy because is a dryland vegetation. The number is very small, but we do say in both sides there is a strong relationship between fog number and the vegetation number, right? So what that tell us, right? So that's basically means the fog impact on vegetation is so big you can even detect that from space, from satellite information, right? So that's never has been done in the past, right? So that's quite exciting, right? So for this one, we didn't see the relationship because we think is because this side actually has a much lower vegetation cover compared to this side. So under this type of a low vegetation cover VOD data, the quality is not good enough to be able to representative enough. So that's always a challenging aspect working in dryland. You work with very small numbers, right? So you have to be very sensitive to be able to see that. And this is from the real image. So basically before, this is the before fog events, this after fog events. Somehow the label is gone. But just give you an idea, even using naked eye, if you look closely, you actually can saw the difference. Of course, it's not big, it's a small difference, but you actually can see that from the satellite image, right? So that's to me, it's a very interesting, right? So because you can actually tell the fog impact from satellite observations. So, but so far, when we look at the impact of fog on vegetation, the vegetation part we got is from satellite information. But for the fog number we got is through from ground observation. So ideally, if you want to do that relationship much more broader scale and more continuously, you should be able to get fog number from satellite as well, right? So that's not easy as well, because there are some sensors they can actually based on the similar as NDVI, you can actually use the sunlight like reflectance to look at the fog. But the problem for that is you don't know whether if you have a satellite on the top, if you have a cloud there, you get the reflection, but you don't know whether these fog events actually touch the ground, this cloud touch the ground or not, right? So because the fog is by definition is a ground touching clouds, right? So that means the cloud has to touching ground. Using regular remote sensing, you can't do that. It's very hard to do. So that's why the next step we did is actually try to think about whether there are some other ways, some newer technologies we can rely on to be able to basically using the satellite to looking at the fog, looking at whether fog touching the ground. So what we did here is there is a less used, but is a NASA satellite called Calypso, right? So the unique thing for this satellite is active. They actually send the lasers, right? So it's not like a pure reflection of sunlight. It's actually active sensor. So they send actually laser all the way through the clouds. So because of that, you have a very high resolution of the scatter. So that means if you have so they give you the ground surface, and then you can actually look at this is the fog events. The white color is the fog events because of high water content, and then you can actually say, okay, here this one. If you look at this location, that's a fog, and this location, that means there's no fog. There's no fog, right? So this is the ground surface, and also. One of the challenge for using remote sensing to doing fog is like mentioned low clouds, right? So because if you have low clouds, they don't touch the ground. From regular remote sensing, you can't differentiate whether that's low cloud or fog. But for this type of instrument, this type of measurement, you actually can say, okay, this actually is a fog event, but here is a low cloud. You can actually differentiate that. The reason you can do that because this is a laser, right? It's not affected by the cloud blockage, and you have very high resolution vertically, and look at the scatter of the signal, right? So this one, all the data we worked is actually all public available, right? NDVI, VOD, EVI, even Calypso data, right? So the only difficult part is this is a very large amount of data. You download, you process yourself. That's actually a very large data amount of data you have to process and be able to look at it. So, but if you can do it, it's very powerful. You can actually looking at the differentiation between fog events and the low cloud events. So after we actually looking at try to detect the fog, we can see how well we did. Right? So in this one. The x-axis is basically the signal from the satellite, the backscatter signal. The y-axis is the ground observation of a fog. So, we can say, we can more or less capture the events reasonably well, right? So it's not perfect. Again, it's R squared 85, right? But it's already big advance you can actually using satellite data directly derive fog water. Right? So that's that is useful advance in this aspect. But limitation for this is for Calypso data. Right? So their laser data is quite valuable, but their like I mentioned, satellite data always has trade-offs. So they have a very low frequency. For our side, we use 10 years data. We only found several data overlap with our station. Right? So that's still in theory we can do it, but in reality, because of the limitation of the amount of data, we still can't do like global application yet. So the last bit I'm going to talk about is, right now we already know fog impact vegetation. We can even see this impact from space. And also we develop ways try to detect fog from space. But then really another big question, we still try to answer is, because we know rainfall is still there, right? Even is a small amount, rainfall is still there. How relative like a fog and the rainfall play a role into the vegetation dynamics? Right? So that's that's a part is still very important. How do you quantify that? Right? So that's the last bit I'm going to touch on. So we basically try to find ways to quantify the relative importance between fog and the rainfall for the vegetation changes. So what we did here is basically based on remote sensing data. So fog is a ground-based data, but for vegetation and rainfall is a satellite-based. So here we use NDVI, like a Moody's NDVI, right? So that is a 500-meter resolution. You have an 8-day resolution. Every 8 days, you have one data point. So for rainfall, we do have a local ground-based rainfall measurement, fog measurement, and soil moisture, soil temperature, wind speed, and we calculate the VPD. Right? So, and then what we did here is besides just using NDVI, we also use the first derivative NDVI. So basically that means you take difference of this day's NDVI from yesterday's NDVI, right? So by doing that, really give us the growth rate, right? How vegetation growth has been changing. It's more rather than the state variable. You have a rate variable. Right? So what we did is, we try to rank the importance of all these variables using random forest. But building on random forest, we can also look at their interaction between these variables. How do they interact with each other and impact vegetation? And here are the results. So this one, the left is the results from NDVI. On the right is the first derivative NDVI. So this figure is made through R package called Vivid. So I highly recommend it. It's quite powerful in terms of the information you can get. So you run random forest first. After that, you can actually look at the interaction between all these variables. That's all the lines represented. So the thicker the line means the stronger the interaction you have between the variables. And then you have the size of the circle, right? So the bigger the circle, the more impact of this variable has on vegetation, right? So that's the meaning of this graph, right? So when we look at NDVI information, when we look at NDVI, we can see actually for cumulative rainfall, right? So the circle size is much bigger than fog, right? So basically we conclude, for NDVI value, actually rainfall is still very important, play a more important role than fog. But when you look at the first derivative, right, we use this one as a growth rate of plants. You can see if you use the growth rate, fog actually play a much bigger role compared to rainfall. Right? So that's actually quite interesting, right? So basically it means for vegetation changes, fog actually play a very important role here. So again, fog actually the power for this analysis is not only tell you how importance of a single variable on vegetation, it tell you how this variable impact others. Right? So you can see fog play a very important role in terms of interacting with others. If you have a fog events, means very likely you change soil temperature, change wind, change VPD. Right? So that's actually give you more comprehensive information, the interaction between all the variables, how do they play together, impact the vegetation. So that's is building on random forest, but more powerful than random forest, give you more information. And then building on this, we can use so-called partial dependence plot, right? So essentially, you control all the other variables. You only allow the variable interest to you to change, and see how this variable changing the parameter you are looking. And for this particular case, we have a rainfall variable, temperature variable, wind speed variable, VPD, and the fog. So we're looking at how these variables changing NDVI. Right? So basically what we saw here is if you think about the total NDVI, right? So the rainfall play a very important role. As rainfall increase, NDVI increase, right? So that makes sense, right? More water, more plant growth. But when we look at the first derivative, that's the bottom. So that's a change of vegetation, basically the vegetation growth rate. When we look at that, you can see actually the cumulative rainfall still is a positive relationship here, but not very big. Actually, what really matters is actually fog events. And so it actually has a pretty strong impact on the vegetation growth. Right? So that's just to tell you, you can isolate different variables and only look at the variables interest to you. That's what the partial dependence plot can tell us. So basically these two together tell us rainfall is still important for sure, but actually fog play a very important role in terms of maintaining the vegetation growth. So that's basically this type of study telling us, this type of analysis telling us. Any questions so far? Okay, so I only have a couple more slides left. So far, what we talk about is fog impact, right? So we talk about the ground observation and the remote sensing application. So we didn't talk about the deal too much, but I just want to point out, deal actually, we have a project right now actively doing 4-year project looking at the deal impact on vegetation from flux tower measurement and hopefully from remote sensing measurement as well. But these slides basically try to tell you is we know temperature is increasing, right? So globally, so that means you increase the dew point temperature. Dew probably will be harder to form. So that means in the future there may be less dew in formation. So, and this one I just want to show here is, this is a global warming experiment. Right? So we know when we try to understand how global warming change the ecosystem, carbon sequestration, or other things, we use a controlled warming experiment to do that. Right? So, but here is a study I was involved. We were talking about if you have a control treatment and a warming treatment, right? The warming treatment significantly reduce the dew formation, regardless what kind of substrate you use, either artificial like plastic or vegetation, or this is a leaf wetness sensor. Right? Depends, regardless what type of technique you are using. So that's all telling us in the future, very likely dew formation will be declining. But that's also tell us, in the past when people doing the global warming experiment, right? So they never really consider dew formation as a part of the process. But in fact, because dew is reduced in that case, that means they may overestimate the impact of global warming on some of the parameters because they didn't consider dew formation, and the dew formation does change carbon flux and nutrient dynamics. Right? So this just gives you an idea how the warming works. So, but that's just the idea about the dew, right? So, just touch on this and talking about what will likely happen in the future climate condition. Under warming, likely will have a less dew formation, right? Really, the last slide is I have to mention is if you, I don't know how many of you guys heard of this fairy circles. Anyone heard of this? Nobody heard of this? Okay. So, yeah, this is one type of vegetation pattern, right? So that's actually, this one is from Namib Desert, from the one I'm working. You can see they called fairy circle because nobody knows exactly how this thing form. That's why they think a fairy make them, right? So that's basically grass circles. So they are maybe 1 meter, 2 meter in diameter. They are different size. And there are millions of them in the Namib Desert, right? So people still try to understand how exactly these circles form and evolve and break down, right? So some people hypothesize that termite is actually the player to form this. Termite eats the grasses in the middle and then form this type of circle. But others think it's not termite, it's actually vegetation itself, is a vegetation self-organization to be able to utilize water and nutrients more effectively. Right? So that's two groups, they try kind of debate with each other. But this one just give you a good example under very extreme environment. Right? There are many vegetation patterns happen. You can use mathematical models to model this. But as an eco-hydrologist, what I try to understand is how this type of vegetation pattern get affected for eco-hydrological process. Right? So that's what we did, the observation. Collaborator is Sujit Ravi. He's from India originally. We went to graduate school together, and he's a professor in another university. We traveled to my site together. We made quite a bit of measurement. Right? So, the big measurement, the major measurement we did is one is the soil moisture. Right? We looking at the soil moisture inside and outside. And also we measure the infiltration rate, how fast soil can go through. We measure the infiltration in the middle and outside. And also, what other things we measure is soil texture, right? So the particle size distribution, right? So basically how fine or how coarse the soil is inside this, in the circle and outside, right? So what we found is that are very interesting is soil moisture is much higher inside compared to outside, and the soil is much coarse, like inside the circle compared to outside the circle, and also the infiltration rate is one magnitude higher inside the circle than outside the circle, right? So based on this, our understanding is, our results we think more supporting the idea of vegetation self-organization. So because the way they do, we think is, when you have a big wind, the wind actually will blow away the fine particles outside, and they will deposit outside and also on the grasses. And then in the middle will be coarse. The soil will be very coarse. So because of that, when you have a rainfall events happen, and water will easily infiltrate inside this soil column, can store there. Water can store there as a reservoir. So then plants were able to utilize that water when environment is very dry. So utilize as a kind of a water pool there. So when we dig up the plant's roots, you can actually say, the roots inside is much longer, outside is very short. So it's actually very long roots and very short roots outside. So it's all kind of supporting the direction. That means vegetation does organize this way to be able to utilize limited water resources, like in this type of environment. Right? So, including fog, because that's a happen in fog zone. So, Yeah, to me, it's just very interesting to think about the nature wonders. How do they form, right? So we didn't solve everything because we know when it happens, that's what happened to hydrology, to soil condition. But we don't know how initially they start, right? So that part we still don't know, right? So it's still worth like further investigation. So just a quick summary for everything I talked about today. So basically using isotope as a tracer, what we show here is fog and dew actually has multiple origins, right? So some come from the ocean, some actually come from the desert itself, from groundwater, and so there are some is a mix, water origin. And also we talk about, we can both soil moisture and groundwater, they actually potential source of water for fog and dew formation, right? So we use a modeling approach to show, you can actually transport the water, right, through groundwater, through relay process to be able to release the water into atmosphere. Right? And also, based on field observation, we can say is fog actually has a pretty big impact on both soil moisture and water potential. And we did develop a modeling framework. We can actually even model the fog control on soil moisture dynamics, right? So the good thing for that is, we can predict in the future, right? For example, based on temperature, based on other parameters, if we know how that will impact the fog, we can use our modeling framework and then predict how much soil moisture will be affected as well, right? So we talk about, we can, based on field observation, we actually show both fog and dew, they can actually increase plant water potential and basically provide some direct evidence that plant can directly benefit from fog water and dew water. But we did saw the timing of the fog does matter, and I show you for the night fog actually doesn't really impact vegetation water potential next day, but for morning fog they have a very big impact. And then we talk about it, right? So fog impact is so big, we can even actually using satellite information from space to be able to look at the impact. Right? So then lastly, we use basically statistical framework, try to kind of quantify the relative importance of fog water and rainwater on vegetation dynamics. So what we saw is if you think about the status variable, like NDVI, so rainfall is actually very, very important, more important than fog. But when you look at the vegetation growth rate, when you use the derivative of NDVI, actually fog play a more important role, much bigger than rainfall. Right? So just give us some idea how rainfall and the fog kind of complementary to each other to be able to maintain the ecosystem dynamics. Right? So that's based on statistic analysis. So yeah, I guess lastly, I just want to again acknowledge our funding source through National Science Foundation. So this is a 5-year grant. So but we did a field observation for more than almost 10 years, and the IAEA for the isotope work, and from the field station, they actually provide a lot of logistics for us for field work. And some group members, they are involved, when we measure soil moisture in the field, we have to set up the soil moisture sensor ourselves, things like this. And there's also student has been working in this project for modeling, observation, and other things. So I guess that's all for the morning first lecture. Any questions? Okay. So yeah, hopefully you'll find this interesting as I do, right? I always think they are understudied. So fog and dew, they are the least studied hydrological component, and nobody cares about them. Right? So I think it's very important for us to be able to have a better understanding. How do they form? Where is the water coming from? How they are changing? That's we require measurement, require modeling, require like other observation. So hopefully some of you guys will be interested and continue this type of research. So again, I'll be around for a little while, and if you have a question about the specific aspect of this, feel free to come to me. We can talk about it. All right, thank you guys. Thank you.
Sir, how can measure the quantity of non-rainfall water?
How do we quantify? Measure it. So for fog, we use fog collector. Like have a picture in the beginning. So this type.
The government and data collecting agency will collect the non-rainfall water.
Yeah. So this one has a very high surface area.
If I want to get the non-rainfall water,
Yeah, you can set up we have plenty of them.
the government have data or not? The government have data or not? Non-data.
No, I don't think anybody collects them. That's why
No one
one collects them. You have to collect yourself. Yeah. That's why it's hard to do. But I think we should do it. Yeah. So it's actually when you look at the hydrological budget, depends on where you are. There could be a significant budget if you miss them, you miss quite a bit of water. So yeah, but
So non-rainfall water is fog, snow, dews.
I mean, snow considered rainfall water.
No considered.
Yeah,
Fog,
yeah.
dews,
Fog, dew,
dews, and
and water vapor absorption.
water vapor, and
That's it. That's only three.
that's this
Yeah.
non-rainfall water.
Yeah. So, but the water vapor absorption is so small. Really, the major player is fog and dew.
If I get data, then I will collect primary data by itself.
Yeah.
If I go through the non-rainfall water.
Yeah.
Thank you.
No, you can identify the error term. Right? One is we didn't use classified. It's unsupervised.
Okay, unsupervised.
Yes.
So you got the data from any source?
We collect them ourselves. All the meteorology variables. No. The weather station is actually public available. You can actually download the data yourself too. Yeah.
Because I was working on my area, so I was not getting. So I have to use the supervised classification.
Okay.
That data was not available. So that's why, because my work is also on LULC future prediction survey. So I was told to do the supervised classification for random forest. I was using Moleskin tool in QGIS.
Okay. So what's your question then?
So my question was that for that random forest, you use
maybe but if a farmer don't have a big field, like in the US, if a small field, they can still do it themselves. So it's not a big investment in that sense. So it depends on how big their field are. So yeah, it's really, if they do by labor themselves, it's almost zero cost. They just harvest all the crop and don't do anything. And then next year you plant yourself. It's actually okay. So maybe you can convince them that way. That means they save by seed. They don't have to plow themselves.
And also they use like so much of fertilizers, chemicals. So like how like we promote them in a large scale to use organic farming.
Yeah, I heard I know maybe in India the same thing. I heard Pakistan the government gave a lot of subsidy for fertilizer.
In India also they give.
Yeah, okay, that's the problem. Then people don't care. They just put a lot. Yeah, I guess I don't. Yeah, I guess I don't know what's the best way. I mean, in US really just government don't have any subsidy for fertilizer. It's very expensive. So farmers, they don't want to waste their money. Right? So yeah, I guess maybe just from policy point of view, you have to talk with the government. Basically say you can still do subsidy, maybe not as much. Then farmers can, also we can do some experiment to show the farmer. Like if you reduce the rate, it doesn't change the yield. If you show them the data, they say, okay, maybe we'll save the fertilizer for next year.
Yes. Like we have to show them visually expert talk and collaboration with agriculture universities institute. Our awareness is not there, sir, in India especially. This is one of the major problem. Because government of India, like they are promoting organic farming and startups, and they are also providing many schemes and fundings.
So I know but agriculture is a huge potential, right?
Yes,
so
sir.
for environmental issues or climate mitigation,
Yes, sir.
there are many things we can do. So that's good to think about that direction.
I want to contribute to society in this agriculture sector, but like I am not getting the idea that how to start all this problem, solution of all this problem.
Yeah, I mean, you can't solve everything. You have to just move one aspect and do it. Right? So like no-till, you can read some papers, maybe write a summary, and give to farmer and show them, that's actually, the yield doesn't change. At the same time, you save a lot of money, you save labor, things like that. And maybe for fertilizer, you can either do some experiment yourself, like a plot experiment, or you just find data from literature to say, if you reduce fertilizer by half, the yield doesn't change. So there are data there. Like in the US, there are people doing that. You can search literature and say, for your soil, you don't need that much fertilizer. You can show them.
But one more problem is there, sir. Farmers are like, most of them are illiterate. So like, I cannot explain them in very technical terms.
Yeah.
So I have to explain them in their local language, like layman, like this is the solution. This much yield you can get if you adopt these strategies.
I mean, you don't need like a scientific language.
Yes.
Right? You can just say, if you don't do the plow, and you actually don't need to do that, like you save your labor in the fall.
Yes.
And, it's actually good for the soil.
Yes.
You don't lose like a soil anymore. You tell them, soil is actually non-renewable resource. And if you lose them, you lose them forever. And so, people don't think about that way, but it's actually, worldwide we have lose so much soil. They form millions of years. When you think about the human lifespan, if you lose them, you lose them. Right? So you can say, for your future generation, so they run out of soil to grow crops. You have to think about that.
Yes.
So I'm glad you think about that.
I'll need your guidance also if like I do some work.
Yeah. Happy to try. Yes.
Thank you, sir.
Sure.
Sir, I want to know how fog and dew is affecting irrigation requirement and at what scale?
That's a good question. I think depends on where you are, right? So if they are not huge, the amount, right? So I think in most of places it probably doesn't affect irrigation because agriculture, you just use a lot of water. The amount of fog and dew probably is a very small proportion. I'm more talking about the natural vegetation. They don't really have outside water sources. So they have to rely on rainfall or fog or dew. For them, it's kind of very important. But for agriculture, people always get water. If there's no rainfall, they use groundwater. Right? So then fog and dew will be very insignificant.
Actually, sir, in calculation of crop water requirement, generally some things like water runoff and this dew and this fog, we don't assume this in the model when calculating crop CWR.
Yeah, yeah.
Generally, we mentioned that its number is too small, so we neglect it.
Yeah, yeah.
But during a time, like in the month, in the December, January,
Yeah.
February, during that time, sometimes it's long hours of fog and dew.
Yeah, yeah.
At that time, we
And
have,
also in summer, I think dew almost every day. I don't know here,
Yeah.
but in many parts of the world, it's like
in general, just like 4 or 5 months, you find a dew.
yeah, yeah. So yeah, I agree. That is actually significantly enough amount of water there, but just nobody calculates that.
Can it be a base for sampling for finding CWR annually or monthly or seasonally?
Yeah.
For example, during in the month of October to January or February,
Yeah, yeah,
at that time, for these 4 months,
Yeah.
we can assume the contribution of fog and dew,
Yeah, yeah.
and we can calculate the CWR
yeah. That would be good.
and
Yeah,
compare with the
exactly.
previous,
Yeah, yeah.
the second.
Yeah, so you can set up this kind of thing for collect fog, and then you can just do like a very cheap if you have a glass put like 45 degree, you can collect dew. Right?
Yeah.
So you can manually collect them in a very cheap way. So then if you do like 3 months, 4 months, you have the data you can prove because that's quite a bit of water.
Can we form a relation with the humidity that how much water can be collected?
We try that. Yeah, that's definitely possible. Yes, it's actually quite a good relationship. But you have to set up
This type of experiment.
you have to set up the relation first. But after that, yes.
Because water is collected in the form of dew is come from air. Actually, available in the form of humidity.
Yeah, yeah.
Come from the air.
Yeah, yeah,
Can be formed with the humidity and dew.
yeah. So
How
I get.
much water can be collected? What is the surface? What is the surface temperature? What is the difference between air temperature and surface temperature that dew is
yeah.
collecting?
Yeah, I mean you are right. There are people that's not my work, but they from just meteorology data, just like you said.
Actually, I missed your session. I came late.
Yeah,
But,
don't worry. So, but yeah, it's possible.
so this type of data is available for doing this type of work.
I guess, yeah, it's available. I mean, it's just not well validated, the data. That you can calculate the data and report the data, but you have to have some measurement to be able to show that is good enough data. So for us, yeah, we calculate ourselves too, but we try to use different ways to validate. For particular site, that you have to validate. So yeah.
Can I get your email ID?
Yeah. You have a piece of paper or something?
I've seen one of your slides where you discuss the interaction between different variables you placed edges and nodes. There was one figure in the presentation. So there was like you that basis we can also have a kind of dynamical setup of the network, and then we can apply those community detection program, and then we can find those substructures which are actually behaving inside very homogenetically way, but outside they are not.
Yeah, well, that's I guess for us, we think about science questions and then we think about tools.
Yes.
Right? So whatever tools can answer our question, we use it, and not, I guess, developing methodology. Right?
Yes.
So to me, I'm not good at that. I'm also about what is my interesting question and what kind of tools. So I guess we think about different.
Yes, and there is one more problem.
Maybe I'll write down my email to you first.
That's what I also think that I require. So idea is like now you have so many climatological variables on every station. So what we do is we kind of compute the distance between them, and that distance is like I mean this is just a simple to say the distance. It's like meteorological. This distance is like one variable minus second variable and the whole square. And then same way for every variable we will do the sum of squares of difference. Take the square. Something in mathematics we call it as L2 norm. So we'll get the L2 norm. If the L2 norm is very less, we'll say that the meteorological variables are, I mean, they are very common, they are behaving in a very close sense, and we can place an edge. But if that value is very high, we'll say that they two are not behaving in the same sense, so we cannot place the edge.
So that's like an information theory. Right?
Yes. And then we can again construct the network, and then we can again do the same thing, and that will be something like climatologically few reasons are same or not. This kind of work has also been done. But if we have good number of stations, good amount of data, we can make few changes and we can go to the advanced level of this kind of analysis.
Yeah, I'd love to talk with you for that. For the station I'm talking about, there's a circle of stations. It's always interesting to know from the information part whether there are redundancies, whether we need a pipe one here or here. So
Yes. And if you want, I can share a few papers with you, I mean, to have a better idea. And so if you think that this same can be implemented in another way, I will be happy to join with you.
okay. Yeah. That should be great. So maybe we can.
Okay, I will definitely, yes. I'll definitely send. I'll definitely
Begin your B.Tech journey. विकास आवाज आ रही है?
हाँ जी सर, आवाज़ आ रही है
चलो
सर। सर एक मिनट सर, वो लाइव स्ट्रीमिंग कर रहे हैं।
अच्छा
जैसे ही हम सर स्टार्ट करेंगे तो मैं जो स्टार्ट हो गया, आप वो स्टार्ट कर दीजिए। Okay. So we start the next lecture. So before starting the lecture, I'll just introduce the next speaker. So we have Professor Manish Kumar Goel sir. So Professor Goel sir is currently working as a chair professor BIS standardization in the Department of Civil Engineering at IIT Indore. He has earned his BTech degree from NIT Warangal, MTech and doctoral degree from IIT Roorkee. He has ranked in top 2% scientist in list prepared by Stanford University in 2020, 21, 22 and 23. He has been awarded the JSPS Fellow, Commonwealth Fellow, Indo-US Wari Fellow, Inspire Fellow, Professor S.N. Gupta Memorial Lecture Award, Best Researcher of the Year 2020, Professor R.J. Garde Research Award, IEI Young Engineers Award, BRNS Young Scientist Research Grant, Young Alumni Professional Achievement Award, NIT Warangal, and several others. His research interest includes impact of climate change on water sources, statistical downscaling, hydrology and glaciology, crop modeling, soil carbon sequestration, data mining, etc. He has published more than 70 papers in prestigious scientific publications focusing on climate change, hydrology, glaciology, and etc. across Indian river basins. Might be more than that papers. He is currently supervising 3 external funded research projects and 13 complete projects as PI and co-PI. Maybe I am not updated with other projects, sir.
चलो
So,
thank you
sorry
Vikas,
for
thank
that.
you. I think we can start now.
Yes, sir. Yes, sir. Thank you so much, sir, for coming. Yes, sir. You can share the screen, sir.
Okay, can you see the screen now?
Yes, sir. It is visible. Sir.
Okay, so good morning. Yeah. So good morning, everyone, and thank you, Dr. Vikas Punia, for inviting me in this Gyan course. So today we will talk about the Ramsar wetlands and how these wetlands are across the India and what kind of risk they have. So you all are in the Bhopal, perhaps offline. You must have seen the Bada Talab. Bada Talab is considered as one of the wetlands or Ramsar wetlands in Bhopal, in Madhya Pradesh, India. So like this, we have more than 80 wetlands or 80 Ramsar sites across the India. And in the last 5 years, there is a sharp increase in the Ramsar wetland across the India because Government of India has done a lots of work in order to identify these wetlands and then designated them as a Ramsar wetlands. So in Madhya Pradesh, we have 4 wetlands, and in Indore, we have 2 wetlands, Yaswant Sagar and Sirpur. They are considered as a Ramsar wetlands. And what we are interested today, what we will talk today, we will try to identify that these wetlands, which are the basically capture the water in terms of groundwater, in terms of surface water for drought conditions, as well as the flood conditions. And they help the urban agglomerations, urban cities, in order to extract the water in case required. Like in Indore, water is being taken from Yaswant Sagar as well as Sirpur whenever is required. So these wetlands, what kind of risk is there in the future? and in terms of climate change, or in terms of climate change, in terms of global warming, because we have seen across the India, across the world, the temperatures are increasing. Once the temperatures are increasing because of increasing the greenhouse gas emissions, and these increase in the greenhouse gas emissions is attributed to various parts or various regions, like increase in the industrializations, because in the last 2 decades or last 3 decades, India has grown rapidly with rate of 8% to 10% GDP per annum. So with this, a huge industrialization has been happened, deforestation, urbanizations, lots of construction activities, uh, vehicular emissions. So many vehicles are on the roads. So all these has been contributed in the increase in the greenhouse gas emissions. And because of deforestation and urbanization, there is a land use and land cover change at many places. And all these things are contributing to increase in the greenhouse gas emissions, and then it is turning to the increase in the temperature. Once it increases the temperature, it impacts our hydrological cycle, because once there is an increase in the temperature, it will intensify the hydrological cycles, and there is changes in the rainfall patterns. And once there is changes in the rainfall patterns, then
Sir,
yeah,
uh, I think slides are not moving. I think you.
I'm on the first slide only.
Okay, sir. Thank you. Okay.
Okay, I'm on the first slide only. So I'm trying to create a base so that we can understand what we are going to talk in next 1 hour or next 1.5 hours. So once there is an increase in the temperature, there is an intensification of the hydrological cycle, and then once this intensification of hydrological cycles will occur, so various kind of rainfall spells will be there. There may be extreme heavy rainfalls, or there is no rainfall. So how these extreme heavy rainfalls will impact the wetlands? What kind of their stamina is there to absorb or to take that water? How these wetlands will behave under the various climate change scenarios or various telecorrections. Like you have heard a terms called El Nina or La Nina or ENSO, El Nino Southern Oscillations. How these wetlands will behave in the next 10 years, 20 years, 30 years, 50 years. For the rest of our life, how they will behave and how their inundation patterns will be there for next 50 years for various return level periods. So that we are trying to understand, because these wetlands are kind of lungs for Mother Earth. How these wetlands will behave. You can see on this motivation on this slide that healthy wetlands are vital for sustainable cities. There is some kind of a study where they say that these healthy wetlands are very essential for sustainable cities. And as of now, we are working on the Sustainable Development Goals, SDGs. These SDGs have been started in 2015, and now we are on 2025. So almost 10 years are done. 60% time has already passed. In next 5 years, what kind of SDGs we can achieve? So healthy wetlands are essential for sustainable cities. East of EM bypass, rainwater reclaims the former wetlands in Kolkata. And in the Bhopal, you can see overflowing Bhopal's upper lake floods Chirayu COVID Center. If you go from Indore to Bhopal, you will find once you enter the Bhopal, in the left-hand side, there is Chirayu Hospital. And in 2020, there is a huge rainfall. And because of these extreme rainfall events, there is an overflow of these Ramsar wetland, Bada Talab. And this Bhoj wetlands, the water has gone into one of the famous hospital in Bhopal. So these are the few news headlines that has come into the newspaper. In addition to that, if you remember that we have a Chennai flash flood in 2015, and in the Chennai flash flood, that has demonstrated how they have destroyed the wetlands, Pallikarnai marsh wetlands, and whole water has come into the city, and there is a human loss of more than 421 lives, besides destroying the flora and fauna, infrastructure, property, farmlands. So this is one of the impact of extreme events on these wetlands. So this Pallikarnai marsh wetland has increased the high rainfall intensity events and led to the extreme weather events and flood in 2015. There is cyclone Barda and then drought in 2017. All these things of flood, drought and cyclones are keep occurring over these wetlands. Another examples I will give you in the northeast part of India, Guwahati. In Guwahati, we have a wetland called Deepor Bill. In the Deepor Bill, it's a kind of freshwater lake wetlands. It will cause frequent flash floods because Guwahati city has been urbanized so much that they are trying to encroach the area of these Deepor lakes. And then the last 2 weeks, majority of the city that has been built because of increase in the population from various places, and because of this, there is a frequent urban flash floods are occurring there. Another examples I will give you the Hirakonda Reservoir, which is located in Odisha. And during the monsoon of 2020, they have witnessed the outbreaks of heavy rainfalls. And these heavy rainfalls have led to the floods. And these floods have caused the severe damage to the service road on embankments, lift irrigation ponds, and field channels. So here I give you the 3 examples of Chennai, Guwahati, and Hirakonda Reservoir. So you can see the impact of these extreme events are happening in terms of homes, property, farmlands, lift irrigation pond, field channels, embankments. It means that these of the events are very disastrous. So as a hydrologist or as a hydroclimatologist, we need to understand the frequency, intensity of these severe events on these wetlands in order to survive for next 50 years, next 100 years, or next 500 years. What kind of events will occur in the future? What kind of measurable action points we can understand or we can take out of these extreme events? So that's one of the focus of this study. Okay, so what we have done, we try to identify the research gaps, and based on that, we try to identify the objectives. First of all, there is an absence of any study of flood-induced heavy rainfall over the coastal wetlands of India. In this, the first part of the presentation, I will talk about the coastal wetlands, which are more vulnerable to all these kind of things. So, in the coastal wetlands of India, is there any flood-induced heavy rainfall? So, there is no systematic study has been done so far in order to investigate the flood-induced heavy rainfall over these coastal wetlands of India. Because if you see, in the coastal area, we have more than 7,500 kilometer length of coastal line. And along this coastal line, there are so many wetlands. So what is happening to these wetlands? So what we have done, we try to investigate the uncertainties in terms of extreme rainfall of return levels using extreme precipitation indices. What is the meaning of return level? That we all understand. I'll not go into the details. We all study in hydrology. But using the extreme rainfall indices. So what kind of extreme rainfall indices are there? Whether how much rainfall is there, 1 mm per day, 10 mm per day, or any kind of cumulative bed days, all these kind of indices we have taken, and we try to understand in terms of return levels. Then the second research gap, we try to understand what kind of threats are there. It means which are the parameters of exposure, vulnerability, and in these coastal wetlands. So we try to relate these different parameters of threat and their interaction with the vulnerability and exposures. And in order to do so, we need to understand the risk label, because IPCC has given a formula, Intergovernmental Panel on Climate Change has given a formula of risk, that risk is equal to hazard, vulnerability, and exposure. So once we understand the risk level, based on these projected extreme events over the wetland, we try to understand using approach, and here we have approached the fuzzy logic approach. And once this has been done, we try to map, or we try to identify the areas which are highly vulnerable to the inundation or inundation mapping in terms of risk of flooding or overflowing. So we will try to do the inundation mappings of high risk level of coastal wetlands using an Google Earth engine. So based on this, using the Google Earth engine, we will try to understand the high risk level of coastal wetlands. Another thing that we try to understand is the monitoring change in the terms of wetland size. What kind of wetland size is there? Whether the 50 acres, 100 acres, 500 acres, 1000 acres. Like if you know this Sundarban wetlands in West Bengal, it's one of the highest size wetlands in India. And Renuka Lake in Himachal Pradesh is one of the one of the smallest size wetlands in India. So how these sizes are being changed over the years? What times of next 20 years, next 30 years? What kind of the trends are there in these wetland sizes because of these extreme events and their patterns? So this is the last one in terms of spatio-temporal changes. So these are the things which we will discuss one by one. As I told you that we are going to discuss about the coastal wetlands. Okay, so we will try to understand these coastal wetlands. If you see my mouse, these are the coastal wetlands we will try to understand. First one is Asatumari wetlands, which is an area of around more than 6,140 hectares. Then is the Bhitarnika and Chilka, you can see here. And then we have East Calcutta wetlands, Koleru Lake, Pallikarnai Marsh Reservoir Forest, Pichavaram mangroves, Point Kelly Marsh, Sundarban wetlands, Thampara lakes, Thane creeks, Vedantagal bird sanctuary, and 4 slides. We need to digitize the areas which are wet and which are dries. Then what we need to do? We need to understand the medians of the wet, you can see it here, and medians of the dries. To calculate the threshold values, we need to compute some kind of threshold value. So medians of dry, medians of wet, and then based on this we will identify the inundation maps. So where the medians are more than wets, we will identify the pixels greater than the thresholds or less than the threshold. We will take them in dry and wet and we'll compute these. So 0 we have taken for dry pixels, 1 we have taken for inundated pixels. So inundated pixels means water is there. Okay, the pixels having the SWIR values less than or equal to the SWIR threshold are classified as inundated, while pixels having the SWIR values larger than or equal to SWIR threshold are classified as dry. So that's how we have taken it, and this is the complete methodology from importing, masking, filling the gaps, selecting the bands, creating the composites, filtering the ears with missing areas and not any bands, and digitization. Once that is done, we will have the inundation mapping. So this is the methodology for inundation mappings. So methodology is done. Now what are the results and discussions for events, different kind of wetland events? Non-stationarity for HRE for wetlands. So these are the wetlands, if you remember. All these wetlands we have put on x-axis, and this is the RX1, RL's return levels. These are the return levels for 20 years, and these are the return levels for 50 years. So this is the return level for 50 years, and these are the return levels for 20 years. And here is the RX1 level from 0 to 800 mm, you can see. But we can identify here. If you see here, this Thane Creek for RX1, this Thane Creek had the highest RL. This is the highest RLs among all these wetlands, from Asthamudi to Bimbada Kool. This is the highest RX1, Thane 1, and this is followed by Koleru. This is the Koleru. This is about 800, and this is about 700. So this is the first results. What about the simple intensity? STI, Thane Creek had highest RLs. For this also the Thane Creek has highest RL, followed by East Calcutta wetlands. This is the East Calcutta wetlands for return level of 50 years. What about the RL10? R10 RLs, it means mm per day. Bemband Kool wetland has the highest RL, followed by Astumadi wetlands. So this wetlands is the highest, followed by Astumadi. This for CWD, Point Calimar wetlands and the bird sanctuary have the highest RLs, followed by Thane Creeks. In terms of CWD, so this is the Point Calimar. This is the highest, and then you have this bird sanctuary and this Thane Creek for CWD. So what is this happening overall out of these all 4 HREs? Overall, when considering all the return periods, Thane Creek, everywhere you can see. Koleru Lake, Koleru Lake, Koleru Lake, Koleru Lake, and the Koleru Lake. East Calcutta wetlands, Mumbai wetlands, and Sundarban wetlands. They have highest return levels, RLs, among all these wetlands. And these finding is also consistent with the previous studies that has been carried out by other researchers in 2009, 2010, and 2021. So this is the first kind of results of HREs over the wetlands. Once we have these HREs, now what kind of risks are there? for these coastal wetlands using the fuzzy logic. Okay, this is the Thane Creek, and here all these wetlands are there that I have just explained. So this is the RX1 for 20 years, SDI for 20 years, return levels, R10 and CWD, and these data sets are from for 50 years return levels. You can see from the region of risk level high, medium, low and unlikely. So the overall risk level assessment revealed that wetlands such as Thane Creek, Koleru, Pallaikarni Marsh Reserve Forest and Thampara Lake are classified as high risk under both RL for our core indices. Okay, so Thane, Koleru, Pallaikarni Marsh and Thampara Lakes, these are considered as high risk for both RLs, 20 years return level period and 50-year return level period at our 4 indices. So the result indicates that 4 wetlands are classified as a high risk, 5 are classified as a medium risk and 2 are classified as a low risk. So if you remember, we have 11 wetlands. Out of 11, 4 plus 5 plus 2, it means high, medium and low. 4 wetlands are high: Thane Creek, Koleru, Pallaikarnai and Thampara. Okay, once we have understood the risk category, let us come to the inundation patterns. What kind of inundation patterns are there in these coastal wetlands? Okay, this is the Thane Creek. Thane Creek, if you see, this wetland has an area of around, let's say in terms of square kilometer, 65 square kilometer is the area. Maximum inundated area is 40 and minimum is 14. How much area was inundated in 2020? And this is the area inundated in 2020. So let us say this portion, whole this area got inundated. So 80 to 100% of Thane Creeks. If I take this Chilka Lake, this whole area got inundated. So these are the various legends, less than 20%, 20 to 40%, 40 to 60, 60 to 80, and 80 to 100%. And these maps generally is talking about the average of last 30 years from 1991 to 2020 of various each pixels. And rest of the things also you can see the inundation patterns of all these wetlands. Okay, let us take one example of Thane Creeks in order to understand the impact assessments. There is one kind of a news study by 2050. Mumbai will see 25% increase in the flash flood intensity. So let's try to understand this Thane Creek in Mumbai. This figure represents a visual presentation of the drainage. You can see the drainage line, drainage stream networks and topographical features. Flood and impact surrounding habitat and infrastructure due to extreme rainfalls. You have roads and railways, you have human settlement here, you have encroachment and you have an international airport here. So this Thane Creek is susceptible to the influence of running water from the flood drains and river beds. So this flood drains and river beds. And the flooding of wetlands are further intensified by the urbanization process of Mumbai city having, including construction in low-lying areas, encroachment on the wetlands, ineffective storm water drainage systems. So these wetlands are facing challenges from 3 quarters. First of all, construction in the low-lying areas, encroachment of the wetlands, and ineffective drainage systems because of urbanization process continuously going on in the city. So you can see these steam networks, you can see international airport, encroachment in that area, roads and railways, human settlements, all these things for impact assessment as one example of Thane Creeks. So what are the key findings for this study? There is uncertainty of the extreme rainfall events over the coastal wetlands have a highest return level period of 50 years that we have considered here. Coastal wetlands, Thane Creek in Maharashtra are more vulnerable to the flash floods due to the heavy rains. Just I have shown you an example. As a result, understanding the impacts of HREs on coastal wetlands in India is essential to appraise the conservation attempts and to improve the projections of flood threats in future climate scenarios. And these findings are useful for the policymakers to assess the impacts and increase in the urbanization or increased area, and we need to understand the best management practices to how to manage the wetlands. Okay. In addition to this, why these coastal wetlands are at higher risk? There is one more thing, that sea level rise. You must have heard that there is a continuously sea level rise because of greenhouse gas emissions, climate change, which is interning the melting of the ice. So sea level rise is going on. So floods are more frequently and for the longer periods of the time. The frequency and the intensity of the storm surges and the tidal floods also increases. Storms and hurricanes, storm surge, high winds, and heavy rainfall associated with these events can cause flooding. Another thing is the erosion. As the coastal wetland erodes, the capacity to absorb and store water decreases. Because once you have erosion, it have lesser capacity to absorb and store the water. In addition to that, there is a lack of maintenance because you have sedimentation, you have debris, it can clog the waterways and drainage systems if you don't maintain them. So sea level rise, storms and hurricane, erosion, lack of maintenance. What are the possible solutions for that? First possible solution that we can think of is restore the natural flow patterns. Restoring natural water flow patterns can help to manage flooding in wetlands by providing an appropriate balance of water inflow and outflow. Because of urbanization and because of the construction in many areas, we have blocked the natural water flow. Once we block the natural water flow, it is creating the problems. There is imbalance for that. So we need to restore that. Reduce the upstream flooding by implementing measures such as retention ponds, natural filters, other green infrastructures. We need to reduce the amount and the velocity of water flowing into the wetlands. So once that is done, we need to reduce the upstream flooding. Construction of water control structures. We need to have some water, we need to have some kind of water balance flow. So once we have this construction of water control structures such as levees, dams, culverts, they can manage the amount of water flowing in and out of the wetlands. And then we need to develop some kind of a wetland monitoring systems. So in order to develop the monitoring systems, we need to put the steam rain gauges, and water level sensors at various levels and various depths, so that we can get a spatio-temporal idea of the early flooding, and that can trigger a early warning systems. So these are the few possible solutions to reduce the risk of coastal wetlands. And these are the few references that we have taken into the study. If you have a question, we can take the question now, or I can go to the part 2 of the presentation.
Do we have any questions? Anyone? No, sir. No one has any questions right now.
Okay. Then we'll go to the second part of arid wetlands. Okay. Okay, give me a moment. Okay. Okay, I can spend some time on this Ramsar wetlands. I hope many of you know. If you don't know, I'll spend few minutes on these Ramsar wetlands. Basically, Ramsar is nothing but one of the cities in Iran. So there's an agreement signed in 1971 on Ramsar Conventions on these wetlands in order to protect and the responsible use of the wetland across the globe. So Ramsar Convention is nothing but the location that is located in one of the part or one of the city of the Iran. In 1971, they have done some kind of agreement to protect and responsible use of the wetlands. If we talk about the area, wetland contribute only 2.6% of the land area, but they play very important role in hydrology and the source of OC, organic carbon, over 20% of the globes. These wetlands are significantly habitat for vital flora and fauna, aesthetic values, cultural values, contain biodiversity stocks with potentially great and pharmaceutical values. These wetlands are invaluable assets for human life with benefits ranging from availability of rare varieties of herbs and plants of commercial and medicinal importance to a great source of the water. So vital flora and fauna, medicinal values, invaluable assets. And now these wetlands are projected to have lost and shrunk over several decades. That's what people are talking about. They are losing the areas. Once they are losing the area, they are threatening the important ecosystems of water refinement, controlled flooding, protection of biodiversity, and supply of the food. Okay, and then these wetlands are vital to address the 17 Sustainable Development Goals of United Nations, which are related to climate change, hunger, health, energy consumptions, and poverty. So, in order to do so, there are 4 strategic Ramsar plans, 2016 to 2024. There they have taken these 4 goals, addressing the drivers of the wetland loss and degradation, effectively conserving and managing the Ramsar site networks, wisely using the all wetlands, and enhancing the implementations. And how they are doing it? Because in the Ramsar conventions of this 4th strategic plan, they have these 4 overarching goals and 19 specific targets. You can see from T1 to T4, T5 to T7, T8 to T13, and T14 to T19. So these 19 targets, specific targets to achieve these SDGs. And in this context of 19 targets, India's ecosystems or India's wetlands, they are most exposed to the climate change projections of temperature rise, changing rainfall patterns, and greater risk of heavy rainfall. So what are the sustainability of Ramsar wetlands in India? That is very important aspect, and coastal wetlands we have just covered. So once we have covered the coastal wetlands, what about the arid wetlands? And the arid wetlands, we have taken the 17 sites. As per Köppen Geiger climate classifications, these areas are arid, desert, and hot. You can see. And these areas are arid, steppy, and hot. Where my mouse, you can see the cursor is there. And these are the site ID as per Ramsar conventions. So you can see 230, site ID number 230. This is Kebladev National Park. Area is 2,873 kilometers. So 230 is this one. So 7,800 and 230 kilometers. And you can see other these wetlands based on this Kebladev, Harike, Sambar. Sambar is this one, 464. Nanji, Nal Sarovar. Nal Sarovar is this one, 2078. Bees Convention, 2408. Vyas Convention. Sursai, Saman, Sursarovar. Sursarovar is this one. Sultanpur National Park. Thol Lake, Vindaj Lake, Khijadia, Rangatitu, Balod, Kanjarikulam, and Chitragudi Bird Sanctuary, 2491. 2491. Here are these all 17 Ramsar wetland across these arid regions, and they are located in different parts of India. You can see all across the India with different kinds of color. We have put Copenhagen climate classifications here, and whichever part they lies, you can understand that we have taken only these arid wetlands. Okay. So to investigate the non-stationarity of heavy rainfall events in terms of return levels over wetlands and arid regions in India. So whatever we have understood till now for coastal wetland, let us try to understand over the arid wetlands and the non-stationarity. So I hope we all understand the concept of non-stationarity. If we don't understand, I can explain in a minute. Non-stationarity is nothing but a, over a period of time, if the statistical properties, it means either mean, variance, if they vary over a period of time of a given parameters or given variables time series, then we will say it's a non-stationarity. It means whatever time series we have or whatever we have the period of for which the behavior of the data is not does not remain constant. It means the behavior of the data will be keep changing. Once it's keep changing, I'll say it's non-stationarity. And in this analysis, we have taken different kind of telecorrections like El Nino Southern Oscillations, Indian Ocean Dipole, Atlantic Multi-Decade Oscillations, and others. We need to understand here whether these return levels and the variability of extreme precipitation has any kind of relation with these indices. Okay, so let us try to understand the methodology. IMD data has been taken from 1951 to 2013 with all these four parameters that I have just explained to you. R1 in terms of mm, STI intensity mm per day, R10 10 mm precipitation in a day, and cumulative wet days. And then we have also taken these teleconnections of ENSO, IOD, and AMO, El Nino Southern Oscillation, Indian Ocean Dipoles, Atlantic Multi-Decade Oscillations. And based on these three telecorrections or climate indices, we have created 56 linear combinations of shape and location parameters. Once we have done it, we have a stationarity and non-stationarity of GEV models, generalized extreme value distribution models. And then we try to understand which is kind of a very good or best covariate combinations in terms of likelihood ratio test. And then we have developed some kind of emission frameworks and then the return levels of various days. Okay, so I'll not explain this slide once again. We have already explained this slide. The same data sets has been taken for arid rainfall regions. Okay, coming to the non-stationarity of extreme precipitation indices in terms of arid region. So these are the names of various wetlands of arid region. So for RX1, if you find out that Nal Sarovar wetland showed highest RL followed by Khijadia Wildlife Sanctuary. You can see my cursor, this is the Nal Sarovar wetlands followed by Khijadia. So this is Nal Sarovar, this is Khijadia. So this has shown highest return levels. And here we have taken the return levels of 10 years, 20 years, 50 years, and 100 years. And in terms of SDI, Khijadia has shown highest RL. This is the Khijadia. This has shown highest RL. For R10, it's Chitrangudi, followed by Khijadia Wildlife. And for cumulative bed days, it's Ranganathu 2 bird sanctuary in terms of this Ranganathu cumulative bed days return levels. And these return levels are 10 years, 20 years, 50 years, and 100 years. So in overall, what's happening? Khijadia Wildlife Sanctuary, Ranganathu 2 bird sanctuary, Sarsai Nabar Jheels, Nal Sarovar, and Thul Lake. They are the top 5 wetlands which have highest RLs across all these return periods. So what is this says? That these findings of several arid regions are significantly influenced by the global climate oscillations, with projected intensifying return levels of extreme rainfall as well as return periods. And the second thing we have done the ranking with help of fuzzy logic. So in terms of ranking, once we have done for the fuzzy logic, the TRIS is nothing but hazard, vulnerability, and exposures. And the fuzzy parameters we have done for very high, high, moderate, low, and likely. Okay, this is the same chart that we have used. 0 we have given unlikely, risk rank 2, low, moderate, high, and very high. And this is the hazard parameters, vulnerability parameters, exposure parameters. 10 years of RL frequency, 20 years of RL flood frequency, 50 years of RL frequency, and 100 years of RL frequency. Vulnerability parameters, supporting services, human settlement, natural systems and water regulation, and annual rainfall days. In terms of exposure, you have crisis ecosystems and observed species. The resolutions are in various forms, vector files or various resolutions. These are the sources and these are data sets. Okay, coming to the vulnerability parameters. So these are the 4 parameters you can see here. All 4 parameters in terms of supporting services, human settlements, natural systems, and annual rainfall days. And out of annual rainfall days, let's say take annual rainfall days, it means the number of days in a year which a measurable rainfall occurs in a specific wetlands. So measurable rainfall is nothing but 1 mm. So you can identify the number of rain days: 10 to 20, 20 to 30, 30 to 40, 40 to 50, and 50 to 75. So in these part little bit, some wetlands here you will find 50 to 70 days. All these wetlands here, this is 30 to 20 days, this is 20 to 30 days. So this kind of vulnerabilities are existing in these wetlands. In terms of exposure parameters, it means you have a crisis ecosystems. Crisis ecosystems, once we say whether you have a vulnerable space, vulnerable things, endangered things, or critical things, or the combination of these. And observed species groups, you have various kind of things: birds, fish, fungi, mammals, plants, reptiles. So all kind of things of exposure parameters as well as observed species in terms of exposed parameters for all these arid wetlands. Now let us come to the risk, how we compute the risk and how we can define the ranks for all these wetlands. Okay, so in this risk rank of wetlands across the arid region, few are unlikely, there is no risk at all, few are low, and few are moderate. It means there is no wetlands which has a high risk or very high risk. So overall risk rank assessment indicates that Sarsai Nalwar Jheel, Byask Convention Center, Chitragudi Bird Sanctuary, Kanjikulam Bird Sanctuary, Rangnathu Bird Sanctuary, and Saman Bird Sanctuary, they are at moderate risk. Few are lower risk. And 5 wetlands, they have no risk at all. So what we have understood out of these wetlands, 17 wetlands, that these wetlands, some wetlands requires moderate risk and some wetland doesn't require much attention. So this is a kind of valuable insights for policymakers, researchers, conservation efforts, for enabling the development for effective strategies for wetland management, disaster mitigation, and climate adaptations. Okay, once we have done, we try to understand what kind of future challenges in terms of trend analysis is there. So for the trend analysis, we have taken the different kind of CMIP6 models for which the resolution is around 0.25 degree by 0.25 degree. These are the model names. This is the resolutions, this is the country, and this is the institute. For future data, AWS S3 Explorer, you can get the future data. Historical temperatures, IMD. Historical precipitations, IMD. Once you have future data from global climate models, you have historical data from IMD. We do the trend analysis using Mann-Kendall trend test, and we try to identify the patterns, whether it's rising, falling, cyclic, long-term movements, short-term movements, or different kind of steps. So you can see the average precipitation in all these arid wetlands. This is the average temperature. So average precipitation in terms of Chitragudi bird sanctuary, Kanjikulam bird sanctuary, Kanjli Ranganathi 2 bird sanctuary is greater than 700 mm, while Samar Lake, Bindwas with less than 500 mm, other wetland they have in terms of 500 to 700 mm precipitations. What kind of average temperature is there? In few wetland, Nal Sarovar and Thol, you have a 33-degree temperature, and other is less than the 33 temperatures. Okay. Now, what we have tried to identify based on two scenarios: SSP, socioeconomic pathways of 245, and shared socioeconomic pathways of 585. Whether these average precipitations are at what range? So average precipitations in Ranganath 32 is close to 500 mm, and Samar Lake is close to 250 mm, and most of the wetlands is close to 300 to 400 mm. And average temperature for Nal Sarovar and Thol Lake is about greater than 36, and average temperature of Ranganath 32, Kanjil, and Bias Conservation Reserve Forest is about 32 degrees Celsius. So this is the temperature range and precipitation range for various scenarios, shared socio-economic pathway scenarios of 245 as well as 585. So what kind of trends are there? Whether they are increasing, decreasing? Let us see it here. Okay. So historical precipitation trends in terms of historical temperature trends. In few of these wetlands, like you can say, this is increasing here, and this is decreasing in these two wetlands. In terms of temperature, there is no significantly decreasing, but there is significantly increasing all three wetlands, one wetlands. So historical temperature is either increasing or significantly increasing in most of these wetlands. What about the future? SSP 245 in terms of precipitation and temperature. So precipitation, you can see in all these wetlands significantly increasing. Also the temperature is significantly increasing. In case of temperature, all wetlands have significantly increasing. What about the next scenario? 585. They are increasing significantly. They are increasing significantly in terms of precipitation, in terms of temperature trends. Okay. Next thing, what we can do, once we understand the temperature and precipitation trends are increasing in these wetlands, so can we use the satellite images for induced flow map to validate the risk, flood risk output? So what we can do for that, we have developed a very simple methodology in terms of we can collect the satellite images, we need to pre-process the satellite data, then we need to extract the flooded areas and flow patterns. Once we do, we'll obtain the flood risk model output, and then we have to be validate, and then we refine and improve the flood models. So based on that, we can develop some kind of a flood mapping maps or flood models based on the satellite data. So what we have done, we try to understand where these flood events has occurred on these wetlands. Like you can see the serial number 1, Kebladev National Park, Bharatpur in Rajasthan. On 15th September 2024, there is a flood events, and this we got the information from internet news. Like Sambar Lake in again Rajasthan, 8 September 2024 and 2019, there is a flood events. Nal Sarovar, there is a flood events. Vyas, there is a flood events. So we try to understand these flood events, and once we try to understand these flood events, we try to map them. If you see, this is the Kebladev map. In 2024, September 2024 and October 2024. So Kebladev, you can see in September 2024, here is only you can see the water. And October 2024, you can see the maximum area got flooded and inundated. So you can see 15th September there was a flood, and after the flood there was only small water, and then it got flooded. Similarly for Sambar Lake in September and October. September there is a water here, and October also this has been increased. Sambar also you can see it here, September 2024 and 19, and this picture is September 2024 and then for October. Likewise, what we have done, we have taken all these wetlands and we try to identify whether the flood that has occurred as per the local newspaper, local media, can we capture that flood in terms of satellite images. So these are the flooded areas where we have taken this. You can see for Chitrangudi in month of June and then in month of July. This is the month of June picture, this is the month of July picture. This is Kanjirakulam. In the Kanjirakulam you can see there is no water absolutely at all, and there is another water. And here you can see we have taken buffer area because the size of the arid wetland is quite less, so we have taken the buffer area. This is for Vyas River Basin, this is for Kanjil, another this is for Rangatittu. Rangatittu you can see September and then the October. Belod, another is Bindabas, Tarsaibal Jheel, Surjeel, Kijadia. Kijadia you can see here there is only small water, and then the water has come up in many areas. Thulke lakes, Harike lakes, Nal Sarovar lakes. So what are the final conclusions? These wetlands can absorb the higher amount of water in terms of Sambar Sarovar, Kebladev, Vyas conservation. In arid regions, flood are beneficial than the disasters. This is a very important conclusion. Because flood are sometimes seen as devastating, but they are vital for ecological roles, including redistribution of nutrients, recharging the groundwaters, and preserving the hills, preserving the health of the wetlands. It is also found that more floods are caused by small frequency of global factors such as ENSO, IOD, and AMO, not seasonal precipitation and temperatures. So these are the few references here for the arid wetlands. With this, if there is a question, we can take it, or I'll give you the one of the demo of Indore wetlands.
So there was one question from your previous presentation. Do you want to ask?
Yes, please.
So how do you validate the inundation area of a wetland in your study?
Yeah, inundation areas. So we take the satellite images.
So sir, on the particular day, how much of it?
particular day we have taken, then based on particular day, let's say there's a rainfall from July to September in a year. On any rainfall, on any rainy day, we will take that image of the day. We will try to identify how many pixels have more than threshold SWIR, because that threshold is based on either 0.5 degree by 0.5 degree, half a degree by half a degree, 30 meter by 30 meter, and each pixel we will identify. Once each pixel have the threshold of more than SWIR, based on that ratio, based on that equation, we will take that pixel as a bat area. And for the each day we will do it, and for each month we will do it, for each season we will do it, and for each season means 1 year, and then we will do for 30 years, and then we will do the composite of all these, and based on composite we will make one single inundation map.
Thanks.
Okay, yeah.
Questions? Any questions, anyone? No, sir. No one has any questions at the moment. You can.
I'll take last one.
Yes.
Indore wetlands. I hope you can see the presentation.
Yes, sir. It's visible.
Okay. So in Indore, we have a 2 Ramsar site. One is Yaswant Sagar Reservoir. Another is the Sirpur wetlands. So this pictures we have taken on 30th November 2024. This picture we have taken for 7th of December 2024. So there are 2 pictures you can see here. 30th November 2024 for Yaswant Sagar, 7th of December for Yaswant Sagar. So after a week's thus times. And if you can see these indices, high chlorophyll content, moderate chlorophyll content, low chlorophyll content, and the clear water. So total area of this wetland is around 800 hectares. High eutrophication area is around 123 hectares. So you can see the changes occurred in these areas. This area you see here, and then this area. So 1 week there is change. Similarly, if I go to Sirpur wetlands, this is the picture image of 30th November. This is the image for 7th of December. Total area is around 165 hectares. If you see in this area, and if you see in this area, there is change. It means eutrophications have been increased. Once the eutrophication have been increased, so let us go one by one. This is Yaswant Sagar. This is the picture of 30th November. This is the picture of 7th of December. So clear water is more, then the clear water has been reduced. Eutrophication level, whether low, medium and high, low eutrophication level has been increased, moderate remains same, high remains lower. So it is observed that the entire sites with 17% of area has low eutrophications on 30th November, which is enhanced to 46% on the 1st of December. So there is a kind of increase. So this is the growing of the vegetable on dried land of Yaswant Sagar using insecticides, pesticides, fishing activities, illegal poaching of birds are affecting the ecosystems of these sites. So eutrophication area has been increased. Let us see the Sirpur. In the Sirpur, you can see the clear water is remain same for 30th November as well as the 7th of December. Low is also remain same. Moderate is okay, and then you can see the high. So it is observed that site has high eutrophication around 56% on 1st of December with similar conditions on 30th November. So what is happening? Due to the discharge of the domestic wastewater into the Sirpur lake, the water quality of the lake are affected and the development of water hyacinth may be observed. So that kind of study is there for Sirpur wetlands. Another thing you can see, this is a Sirpur, whole Sirpur, and this is the Indore Dhar road. Here are the residential areas. Lower Sirpur Lake, there is under construction STP. This is the Upper Sirpur Lake, and this is Devi Ahilya Sarovar Udyan. So Lower Sirpur Lake is highly eutrophicated compared to Upper Sirpur Lake. This is less eutrophication. Here is the high eutrophication. So this is some kind of a water study of water quality study of real time of these Indore lakes in terms of uh, high chlorophyll content, moderate chlorophyll content, low fluoride content, and clear water in terms of NDCI. So this is a real kind of observation system that we are planning to develop. For every week, we will give the data so that wherever eutrophication is more, wherever there is a requirement of human action, that can be done. This will help the manpower, time, and energy. So that kind of work is still in the process. So with this, I will come to the end of the presentation. If you have any question, you can ask out of all these three presentations on the wetlands.
Thank you, sir.
Thank you.
Any questions?
Sir, I have a question.
Yeah.
How can we conserve Bhojtal wetland of Bhopal? Because the overall surface area of upper lake is also decreasing day by day.
I think that's a very good question, and that's very pertinent as on today. Bhoj wetland, I have shown in one of my presentation. In the first presentation, I have shown that there was a huge rainfall in 2020, in August 2020. Water has come up and it has inundated the Indore Bhopal road as well as the Chirayu hospital. So first problem is coming the encroachment of these wetlands. Because of human settlement and many other areas, the encroachment has been increased. Second thing is coming the agriculture activities, they are going on in these wetlands. So agriculture activities, farmlands have been created and these wetlands areas has been increased, wetland areas has been reduced or even shrinkage. So you have urbanization, you have encroachment, you have a farmlands, and there's huge kind of sedimentation is coming. The sedimentation has to be reduced in order to increase the base flow, in order to increase the overall process or overall profile of the wetlands. So these are the few measures we need to take it up in order to maintain the same area or in order to increase the area.
Any other questions, please? Okay, sir. So thank you so much, sir.
Thank you, Vikas. Thank you so much.
Sorry. Thank you so much for giving your time from the busy schedule, and I think they have got insights on the wetlands, so they may start their work on the wetlands also. Thank you so much, sir, for your time, sir.
Thank you so much. Thank you, everybody.
Thank you.
इसकी ये उसके लिए होगा ना, उस ऑनलाइन उसके लिए। ठीक ठीक है, चलो। So okay, we'll start this session. So in this particular sessions, we will cover the concept of hydrological modeling, and we'll see how we can develop that soil and water assessment tool that is particularly used for hydrological modeling, simulation, and all these things. So before going to particularly that SWAT models, we'll cover the basic things related to hydrological modelings. Like we should know what is the catchment and what are the characteristics of catchments. Okay, how means hydrological simulation models works, what types of equations they use. We will see all these things. So I think, and then we'll go for some kind of a case study, how you can incorporate the climatic data, what you have seen you have gone through that through the IPCC. You might have heard about that CMF 5 data or CMF 6 data. Have you heard that CMF 5-6 data? Coupled model integrated phase 5 model data, that GCM data, RCM data. So before using that data, or how we can incorporate these data in SWAT models, how we can develop that SWAT models or hydrological models, we'll see in this particularly in these lectures. So basically, what are the steps involved in SWAT modelings? We'll see what types of data is required, how we can prepare these data sets related to particularly SWAT models. Why we are using SWAT, we'll also discuss, and then we'll see one case study in which we have applied different GCM data, and then we have developed different scenarios, like you might have heard about RCP scenarios, reconcentration pathway scenarios. So we'll discuss during the case studies. So basically, first we'll see what is catchment. Can anybody tell me how do you define a catchment or a watershed or a basin? So I think you all of from hydrology or geology background, so you might have heard about the term related to catchment. So can anybody define me? What is catchment? Yeah, the land area which is draining to a particular the river systems or a channel systems at a particular locations, that is known as your watershed. Yeah, or basins or sub basins catchment. That we can means there is a not any hard and fast rules to call it as a watershed or sub catchments, but different country named its watershed or catchments like this. Or sometimes we may also define based upon the area. So as we are able to see this in this particular figures, whatever the rainfall which is taking place above this particular area, how much amount is going to collect at that particular outlet, that is the area is known as your catchment area, and that boundary which separates two adjacent areas is known as your ridge line. Okay, so whatever the amount of rainfall which are occurring in this particular area would be goes in two different directions. So some part of the rainfall will go and will takes flow in this particular area, and some part will go in the adjacent area. So every catchment is having some kind of a adjacent boundaries also. The ridge lines is the dividing lines of the catchments. Yeah, water divided lines we can say. And or we can also define it as a natural boundary. Like you have an administrative boundary in a maps or on this district boundaries, state boundaries there. So watershed or the ridge line or the water divide line is the natural boundary, and this is the smallest unit where any hydrological models work. So at these level, like at watershed level, it computes all these types of your water balance equations. Whatever you have gone through in this particular course, you might have gone through that what are the water balance equations, how inflow and outflow is taking place within the catchments. You know about the water balance equations? The concept of water balance equations? Yeah, the mass inflow minus mass outflow, that is equal to change in the storage. And the inflow, whatever the inflow which we are getting, most of the times it is in the form of precipitations. Precipitation itself having so many types, like in the form of snow we are getting, like in the form of rainfall we are getting, sometimes in the forms of hails, and some other forms is also there. So in different textbooks you will get all these types of informations. So at particular that catchment level, we are computing how much water we are getting and how much that water is converting into runoff, or how much water is converting into groundwater recharge, or how much water is going as a evapotranspiration or interception. The complete water budget equations will do at the catchment level only. Okay, so this is the basic unit where we start our things. So for that, doing all these things, we require some kind of a tools. Okay, so that tools is covered in a that hydrological models is known as hydrological models. So basically what we are doing, we are using some kind of a tools that is known as hydrological models. So basically they are the simplified representations of your physical phenomena. Okay, what they are doing, that basically hydrological models are doing, they are simplifying your physical phenomena with the help of some kind of a mathematical equations. Suppose that Manet campus, if you are taking the example of Manet campus, the boundary would represent as a ridge lines, and within that boundary how much rainfall we are getting, and the land use and the types of soils, how much they are converting or they are contributing, means to generating the runoff or evaporation or the storage, would be your means physical phenomena that is taking place within that closed boundary, and then how they are interacting with your land use and soils and all these things. So all these types of things we can capture with the help of some kind of a models. So they are simplifying our natural processes. Okay. Then the terms is simulations. So basically simulations is we can say as a copying or the mimic. They are mimicking means some kind of a natural processes. So whenever we do some kind of a modelings, we require to do some kind of a simulation with the help of some iterations and all these things. Then we have different types of models. We'll see that also. So basically that hydrological models are the combinations of equations, maps and the database. So as we discussed already, that hydrological models are the combinations of mathematical equations. Like you might have heard about y equal to mx plus c. It itself is a one kind of a models which gives you the slope of a line. You might have heard about the rational formula, that is q equal to CIA. Right? That is giving you the peak discharge values. Okay? Then by using that these kinds of mathematical equations, or sometimes we use, most of the times nowadays every hydrological models are working or using GIS as a platforms. So for that we produce some kind of a maps, and as well as we produce some kind of a database. For that we require some kind of a data. We'll see SWAT, in SWAT, particularly in SWAT model, there is a large number of data set is required. Okay, with the help of that, we also should know about the database management systems, about some kind of a Microsoft Access things we should know, because we have to do some kind of a database management things, because we have to create our own data sets if you want to build hydrological models for your study area and all these things. And then the output which we will get in the form of maps, that georeference map or geospatial maps, that will capture the spatial variability within your catchments, like how much runoff is taking place or how much evaporations is taking place. You can spatially map those particular processes. So basically that hydrological models use mathematical equations, and then mathematical equations represent the processes. What are the processes are taking place? Like runoff is one of the process, evaporation is one of the process, groundwater recharge is one of the process, and that processes is captured by some kind of a parameters you have to use. That is your calibration parameter. We'll go step by step in that also. So that parameter, the understanding of that parameter is also very much important, because simply developing a hydrological model is not a very big task, but doing a calibration, it's very tricky task as well as the very tedious task, because unless otherwise means you don't have the complete knowledge of what processes are taking place in your catchment area, you won't be able to do the calibration part. So that is why you should understand what is hydrological models and what is hydrology, what is water balance equations, how. In the previous lectures, I am not going in details to water balance and all these things. I think they are already covered in this training program. So this is the one of the examples of your watershed models, like how we can create the catchment area or ridge lines. This is the examples of the upper lake of Bhopals. This is the Badbadra Dam and Kaliasot dams. These are the output locations. With the help of some kind of a GIS softwares, you can create these types of a watersheds or stream networks. You can compute the streams orders or the geomorphology of the complete geomorphology. What are the area of this particular catchment, the streams orders, stream length, how the tributaries are contributing to that. If you have that rainfall and land use and all types of other data, you can use in that data in particularly any models, not only in SWAT, in any models, or you can generate the statistics. So basically that hydrological models are divided into two parts. One is the deterministic approach, and then second one is the stochastic approach. So in deterministic approach, again it is divided into lumped and distributed. So can anybody tell me what is the lumped model or what is distributed model? Yeah. As a single unit. Can you give me the one of the example? Like you might have heard about the unit hydrographs, synthetic unit hydrographs. So they consider the complete catchment as a one unit. So they don't consider the spatial variability. So that is known as your lumped models. And what we do in distributed models, we divided the models into several parts. Like when we go to that SWAT particularly, that is also divide that catchments into sub-catchments, and then sub-catchments is further divided. We'll see that also. So that approach is known as your semi-distributed approach. Semi-distributed, in particularly SWAT. If we divide that particular catchments into a number of cells, that is the fully distributed approach. That is being used in WIC models or Mike SHE models. They use the fully distributed models. In that case, we have to predefine the cell size. Accordingly, it will compute what would be the cell size, what would be the number of sub-watershed and watersheds in this, in your particular watershed. So at that particular level, it will compute the water balance or water budget equations for your catchment area. And then again, it will aggregate to the sub-basin scale and then to the basin scale. And then it will provide the average, basin average values. Means suppose you want to compute what is the average rainfall is your catchment is receiving. What are the average runoff your catchment is generating. So that distributed or semi-distributed approach is used. Then again it will divided based upon the types of flow. Steady flow, one is steady flow, you might have heard about in fluid mechanics books and all these things. Then another approach is stochastic models. So in that stochastic model, that is related to basically your climate model, GCMs, RCMs. They use the concept of probability as well as the randomness. How randomness means, because nature is very random, so we can't predict very accurately. That is why whenever we do some kind of a climate change modelings and all these things, I'll show also during my case study, we'll use 4, 5 or 5, 10 or 15 different types of GCMs, global climatic models or journal circulation models, we can say. We'll use different models because their inputs are different. So we are not able to identify which models is predicting well for our study area. So then we'll go for another technique that is known as your ensembling of the models, ensembling techniques. So we'll go that in your subsequent slides that also. So then the question comes, how do we select any types of models? Why we are interested in SWAT? Why not in HACK-HMS or WIC model or any other models? So can anybody tell me? So what are the criteria to choose the particular models? Why we are not doing on HACK-HMS? Because simply HACRAS or HACK-HMS is also a model which are used for rainfall runoff modeling. Okay. We can say event-based models or purpose also. Yeah. What you are saying? Depends upon parameters, depends upon expertise, depends upon data, depends upon the requirements. And then why we are using SWAT? Because That HECRAS, Mike SHE, all these are the means event-based models, or they are generating some kind of a runoff. But the advantage of this SWAT model is these are based on your management practices also. You can incorporate different types of management practices which are taking place in your particular catchment area, like what are the irrigation means cropping patterns you are using, what types of irrigation patterns you are using, what types of land management practices are being used in your catchment area. You can give input in your SWAT model also. So that is the basic requirements. That depends upon what types of studies you are going to do. And while doing these types of studies, we should know some catchment characteristics, like what are the topography, what are the shape of the catchment, size of the catchment, then land use of the catchment. Why? Because they all are governed the runoff characteristics or as well as the runoff volume. How topography would that cover the runoff characteristics? Because wherever you get the steep slope, you will get the means more runoff generation, or the lag times, your time of concentration would be less. Then again, shape is also would be one of the major factors which contributes in runoff volume generation, the quantitative size. Similarly, then the soil types. Again, the runoff characteristics would majorly depends upon the type of soils. Like if you have gone through that any engineering hydrology books or hydrology related books, they have divided that 4 types of hydrological soil groups is there. That is A, B, C, D. So how they have classified that A, B, C, D group? Which type of soil would give you the more runoff or less that infiltration? Yeah. Okay. So let's talk about the type soil hydrological soil group which is having that group A. So it will generate more runoff, or infiltration capacity would be the more runoff. Or what about the hydrological soil group D? Yeah. So curve number is one of the parameters. That SCS curve number equations, you might have heard about that SCS curve number methods, in which that is also used in SWAT model also. One equation is also there, that is known as your green-amped equations. That is also being used. Provided for that green and amped equations, we required hourly data or sub-hourly data. For SCS curve number equations, we will use the only daily rainfall data and all this thing. So these are the some parameters which we have to incorporate, or these becomes the input parameters for your hydrological models. Like types of land use is also affect your runoff generation quantity as well as the quality. Suppose if you are using some kind of a means models in your urban catchment area, so in that case particularly SWAT model might not work as well as it will work in a agricultural catchment area. So basically SWAT model is developed for agricultural catchment area only. So for urban catchments and or for to simulate the urban storm hydrology, will go SWAT or some another kind of model is there, or some kind of means you can use empirical equations that is developed for regional scale, like rational formula. So all the design parameters which is used in your sewerage designs or pipeline network, that is based on your rational formula only. That they compute the peak discharge values during the monsoon season and all like this. So these are the some parameters which we have to keep in mind while doing the modeling parts. So this is your complete hydrological cycles which might you have seen. So as precipitations or rainfall taking place, so once the your infiltrations that requirement is fulfilled, then the surface runoff will take place. From that surface runoff, you all know that evapotranspiration will take place. Then during that your infiltration parts, it will go deeper and takes part into the groundwater recharge. That groundwater becomes your base flow, and then base flow again contribute to your surface runoff. Based on that, we divide our rivers into perennial or non-perennial rivers. You might have heard about the perennial rivers, non-perennial rivers. You know how that perennial rivers are getting waters? Through the base flow only, throughout the years. Yeah, in perennial rivers we are getting water throughout the years. The main source of the waters for the perennials is the base flow. Okay, then some kind of a losses is also there, interception losses is also there, transmission losses is also there. So all types of this water balance we can compute in a software, or in today's tutorials, by the end of this lectures or the tutorials, we will compute the complete this hydrological cycle for our basin soils. Whatever we are seeing in this will show in that particularly numerical values. It's like if we are getting 1000 mm of rainfall, how much rainfall is converting into runoff, how much that 1000 mm of rainfall is converting into groundwater recharge, or like that will show you. So while doing that particularly modeling parts, so some general procedure is there. We'll quickly go through that, and then we'll start the requirement of SWAT model and all these things. So the very first step is that identifications of information required for management decisions and all these things. What types of data you have, or what type of modelings you want to do. Like suppose in case of groundwater modelings, if you want to do, so you have to acquire the knowledge about the what are the groundwater wells is there, what are their depth is there, and what are the other parameters like types of soil is there, land use land cover, what types of land use land coverage exist there, or the hydraulic conductivity of the wells and the soils and all these things. Then you have to develop some kind of a conceptual models also. That is based on your experience or what types of mathematical equations you are going to use. What are the physicals process are taking place within your catchment area. Based upon that, you can use the already developed mathematical models and like that. And then you have to define some kind of a boundary conditions or input data and all these things. Then we'll go for model development. Then once you have collected, you have established what types of mathematical equations you are going to use or what types of data you are going to use, then you can go for model development phase. And then once you have developed, then you have to check the outputs in the form of what types of output you are getting. You have to match that output with your observed data. Like as we have seen the catchment boundary and all these things, catchment definitions, and then we have defined that at a particular outlet point. So sometimes in that particularly catchment outlet points, we have some kind of a measuring devices or measuring techniques is there. Like in India, that Central Water Commissions is doing. In the first lecture, they have mentioned Aditya sir. They are monitoring the discharge, and that particular location within that catchment is known as your gauge catchment. Ungauged catchment is also there. For that ungauged catchment, they won't measure. Some kind of a wear or some kind of advanced techniques is also there for measuring the discharge and all these things. So once you have developed your models, you have got that output, then you have to match that output with your observed data, and then you have to compute some kind of a statistics. That is known as your model calibration. So basically what you are doing, so you are trying to match whether your predicted or simulated output is near to your observed output or not. You have to basically you are trying to figure out the difference, what type of difference you are getting. Like that, you have to plot these types of hydrographs between your observed and simulated data. So you might have seen all these types of graphs in your research paper. Okay, this is your discharge, this is versus your time curve. So you have to suppose this is your observed data or this is your simulated data. So you have to identify what type of gaps you are getting, or is kind of a shifting is there, like that. And then you have to compute some kind of a statistics in the form of R square, in the form of net Shetcliffe efficiency or percentage bias, like that you have to compute. And then you have to compute the model performance. If your model is performing satisfactory, then you can fix your parameter. Otherwise, you have to adjust your parameters. That process is your model calibration process. So that is one of the most tricky part. That is why you require the complete knowledge of hydrology. Otherwise, you won't be able to do calibrations. If you don't know about the curve number methods, then how would you identify? Curve number is the functions or dependent upon the land use as well as the soil types, and the management practices, whatever management practices is taking place in your catchment area. So you must know the hydrology as well as your catchment areas also. Then if you talk about some kind of evaporation equations, there are 3 equations there in SWAT model also. Like you might have heard about that Penman-Montet equations. So that Penman-Montet equation requires huge number of data. Every climatic data, whatever you have heard, would be used in Penman-Montet equations, like solar radiation, wind speed, wind velocity, relative humidity, solar radiations, everything is required. So it's a very complicated equations we can say. Then the second is Priestley-Taylor equations. Some parameters have been omitted from that equations. So some less parameter is required for Priestley-Taylor equation. Then the third one is Hydrometeorological equations. In that equations you requires only solar radiations values or minimum maximum temperatures. Based on that solar radiation and minimum maximum temperature values only, it will give the evaporations values. So like that, if you have the knowledge of hydrology, then only you will be able to do such kind of analysis. So all these equations having some kind of a coefficients. That coefficients is your parameters, which you need to adjust during your calibration parts. Okay, and all these coefficients having some kind of a values, minimum values as well as the maximum values. Like if we talk about curve number, that curve number itself having some kind of values that is varying from 0 to 100. 100 means completely paved area. Your means rainfall directly converted into the runoff, like that. So if you have 70, 30, in K. Subramanya, they have given the complete table for that curve number with their possible range as well as the land use type and the soil types also. So in engineering hydrology book. So like that we have to understood the groundwater parameters also. So in particularly SAT model, there are around 50 parameters there for your discharge calibration. If you are working in snow feed watersheds, then you have to incorporate the snow parameters also. Like what is the lapse rate, how temperature is varying, what is the snow means what percentage of rainfall is getting in the form of snow, like that. All these types of inputs we have to give. So that requires very extensive means knowledge about hydrology as well as the catchment characteristics. Once you have done that calibrations, basically in calibration what you are doing, we are doing some kind of a trial and error or some kind of a fine tuning. We are trying to match our observed data graph with simulated data graphs. The ultimate goal of calibration is this. Once we satisfied, what happened in this case particularly, we don't bother about the actual hydrology or actual processes. We just focus on that we have to match this observed and simulated. So we every time, most of the times, the students do over calibrations. So they are getting very good results during the calibration periods. Once they go for validation periods, they are not getting good statistics. So there are some values already defined for these statistics. We'll go through that also. So once you are satisfied with that statistics, you stop your calibration and then you go for validation parts. So during validations, what we have to do, we have to give some kind of a unseen data. So like when we do some kind of a calibration and validation techniques, then we have to divide our data sets. Suppose you are running your models from 1960 to 2024. So then you divide your data sets, some parts around 60% you keep for your calibration part and 40% you keep for your validations part. So like that we have to do some kind of a calibration and validations. So once you fix your parameters and then you provide some kind of unseen data to your models, and then again you have to compute the statistics, whether these statistics are coming within the range or not. So then only you decide, okay, my model is giving satisfactory results. Now I stopping the calibration and validation part have been done. Then you go for scenario generations. Okay, then we will use some kind of a GCM, general circulation or general climatic models. Their output will use, then we'll go for predictions. Like I'll show in my case study, we have predicted till the end of this century, like 2100. So we have divided all this data range into 3 parts: near future, mid future, far future, like that. Then we have to see what are the changes has been taken place during the by the end of the century within my catchment area like that. So this is the overall pictures like that we have to do. Then one terms is also there, the uncertainty analysis. This is one of the most important part we have to do again in hydrological modelings. So we'll see during that model validation and all these things. Then we'll go for scenario generation, then model uncertainty analysis, then report writing, conclusions, and all these things. So this is the overall steps which you should use during your modeling part. Whatever models you are using, these are the common steps. In every models we have to follow these steps. Then some limitations would always be there, like you won't be able to capture the complete phenomena, like some models won't be able to capture the peaks, some models won't be able to capture the base flow phenomena and all these things, depending upon their data limitations and other requirements. So these are the some major hydrological models you might have heard about that. Hydrological simulation programs, Fortran, HPHS models, then HECRAS models you might have heard, Mike models you have heard, and then soil and water assessment model is there. So these all are given model types, their parameters with lumped, distributed, and all these things, continuous models. So basically we are interested in SWAT models, so we'll discuss only SWAT model only. So now come to the SWAT model. So basically SWAT model is a continuous models, physically based, semi-distributed. By mistaken I have written distributed, it is semi-distributed. Okay, then process based model, physically based models, then that simulate the management practices, as I said. Why SWAT is different from any other hydrological model? Because of this, because it simulates the management practices also, provided you should have the knowledge where and how to give that management practices in the particular SWAT model. Otherwise, simply you might have done that previous exercise in rainfall runoff modeling, some kind of regression equations you have used, or you have directly generated runoff using the rainfall data and in these things. Even in your ANN modelings also, they are known as your black box models. You just have to provide some kind of rainfall data, and you have to provide some kind of rules, and based on that rules it will automatically create runoff, and it will create some kind of statistics and all these things. But in this particularly models, we have to provide land use informations, soil type informations, slope informations, as well as the weather data. So whatever processes are taking place within our catchment, we have to provide all the information to this particular models. That is why it is being used, almost one of the most widely used software in the field of hydrology. The another reason is freely available. You don't require to purchase its license versions, or if you are working on QSAT or QGIS, that is completely free, so anyone can use. So like that, what it can simulate the hydrology of the basins, like that, whatever precipitations or rainfall taking place within catchments, how it is going to convert into runoff, evapotranspirations, or storage, groundwater recharge, like that. It will also do the stream routing. It will use the Muskingum method or variable coefficients methods for your stream routings. Then sediment erosion is also taking place within the catchments, can be captured by SWAT model. Then for that sedimentations computations, it will use universal soil loss equations. You might have heard that modified universal soil loss equation would be used in SWAT models. Then somebody is interested in plant growth or nutrient pesticide cycles, agriculture management practices, if they have the data related to crop management, what type of irrigations, what type of crops are growing in your catchment area, what type of irrigation practices is there, they can be incorporated in SWAT model as an input, or will get the output like that. So these are the ultimate output of SWAT models. Okay, so now come to the working methodology of SWAT, how SWAT model works. So basically SWAT requires 4 types of inputs. 4 types of inputs is required by SWAT model. That is the very first input is your DEM data, that is your digital elevation data. You will get all these types of data, mostly data from the remote sensing. So yeah, so for that you can use SRTM data, you might have heard about that, or you can use some kind of a Astra data, or you can use that Cartoset data. They both are from USGS you can get, or you can get from Bunidhi. Then the second input you require, that is your LULC information, that is land use land cover change information, or land use land cover informations you require. So with the help of again GIS softwares and remote sensing data, you can create that LULC. If you don't want to create, I'll show the links and some kind of inputs you can create. Then the third information you require is your soil data informations. Okay, so what you can do, you can directly use the soil map that is prepared by FAO, Food and Agriculture Organization USA. They are providing the raster image of that particular for the complete world soil data is there. With the help of that, you can create your own soil database. But yeah, that is the one problem, and second problem is that that is available at a very coarse resolutions. So in that case, you can do for your initial model building, or to understand how your model works, you can use. And once you get some kind of a confidence how to develop that models or how to run that models, you can go for NBSS LUP maps, National Bureau of Soil Survey and Land Use Planning. They are providing hard copy maps. You have to digitize that maps, and then along that maps you will get some kind of a booklets. From that booklets, some manual types of books you will get. From that manuals, you have to extract the soil properties, like what are the soil types is there, what are the hydraulic soil group is there, what are the number of layers they have incorporated, what are the hydraulic conductivity, what are the anion information, cation information, what are the information required by soil database. You have to prepare your own database. That is the only way. Otherwise, you can, if your catchment area is small, you can go into the field, or you can collect some kind of a soil samples. Or some readily available tools is also there, like soil pseudo functions. One software is also is there. If you have some samples within your catchments, you can give that samples to that particular software, or they will generate with the help of interpolation techniques and other techniques. They will generate some kind of a statistics or some kind of a properties, soil properties, other properties related to your water catchment area. So these are the third input. The fourth input you required is your weather data. So in weather data, mostly you require that rainfall data, temperature data, or your wind speed, solar radiation, relative humidity. If you don't have wind speed, solar radiation, relative humidity data, only rainfall data and minimum maximum temperature of the day is sufficient to generate or to simulate the hydrology of your catchment area within SWAT models. Okay, so you have to keep in mind that at least rainfall or temperature data you should have. Rainfall data in the form of daily data, and temperature data in daily data, maximum minimum temperature of your daily rain data. Then other data you required, that is your observed data. Observed data, like if you are computing, you are observing, means that the statistics of between observed and simulated data with the help of discharge data. So in that case, your observed data would be discharged. You can compute your model output with the help of evapotranspiration data also, or some kind of a satellite is there, GRACE satellite you might have heard. They are also providing some kind of a soil moisture data readily available. So if you have soil moisture data or evapotranspiration data or some kind of a groundwater data, so you can do calibration with the help of these observed data also. Yeah, sediment concentration data can also be there. So then in that case you have to, if you are interested in sediment concentration, then the SWAT is also providing sediment concentrations also in gram per liters, or shayad in gram per liter is their unit, yeah. Or if you are interested in load, then you have to convert your observed data into load. You have to multiply it with velocity, and some kind of a coefficient is there that concentration data would be converted into load. So these 5 types of data you required. So basically from digital elevation models, it will compute the slope, and then based on the slope, it will compute some kind of a flow direction, flow accumulation. Then ultimately it will create the basin boundary, and then that basin boundary would be further divided into sub basins. Okay. Then from LULC map, then it will use the LULC map, then the soil map, and then basin boundary. Again, it will means that break your sub basins into some kind of a smaller units. That smaller unit in SWAT, that is known as your hydrological response unit. This is the smallest unit at the particular that SWAT model work. Okay, so that at this level, at HRU level, it computes some kind of a water balance. For that, it requires some kind of a climatic data. Climatic data, as we discussed, in the form of rainfall or temperature data it will use. Then it will compute the water balance equations for at a particular HRU. At a single HRU, it will compute the water balance equation, that what are the inflows taking place in that particular HRU, what are the outflows taking place, and what storage is taking place in that particular HRU, it will compute. And then again it will aggregate all these HRUs at the sub-basin level, and then it will aggregate to the basin level, and then it will give the output, as I have shown in the previous slides. Whatever the precipitation is taking place, or what are the precipitation is converted into rainfall or runoff, and like that. Then we have to run the model. So these are the steps. The first step is we have to create this is the first steps, basin, sub-basin. Then the second step is the create HRU. Then the third step is the means we have to run the model, and then we have to identify that calibration and validation parts we have to do. During that, after running that models, I'll show you that that module is there, edit SWAT output. In that particular edit SWAT output, we have to provide the management practices. What type of management practices is taking place, or if we want to do, if we are interested in reservoir modelings, we can incorporate here in these terms. Once we satisfied with that, all these input parameters, all this are working well, and we'll go for run model, and then we'll go for calibration and validations. For that, one terms is also there, sensitivity analysis. As I have already mentioned that for discharge calibrations, we have around 50 parameters. So all the 50 parameters might not be useful for our calibration purpose. So we have to reduce these parameters, so we can do some kind of a sensitivity analysis. So again, there are different types of methods is there doing sensitivity analysis, or for that calibration, sensitivity analysis and validations, there are stand-alone software is there that is known as your SWAT CUP, calibration and uncertainty program. So once we have completed these types of steps within that SWAT models, we bring that output of SWAT model into the SWAT cup, and we'll do calibration, validation, and all these things. And then once we satisfied with that, we'll stop the output, and then we can go for scenario generation, or we'll use the GCM, RCM outputs and all these things, or we can do predictions like that. So this is the simplest methodology I have presented, but it is not as simple as it is looking. So this is the water balance equations which is being used by SWAT models. Basically, this is your input, or these all are output. This is your precipitations, this is your runoff, evapotranspiration, groundwater recharge, and change in storage. So basically, this equation is being used in your SWAT models. Then SWAT is basically a combinations of multiple models. As we have already discussed, that hydrological models are the simplification versions which we are using, and these are the combinations of mathematical equations. So SWAT itself is a combination of different types of sub-models. Like I have already mentioned, it uses SCS curve number method for your runoff computations. We are not going into details because all these details are already given in your textbooks and all these things. You can refer directly, or even SWAT manual also, all this information is given. I'll show that on SWAT website also, everything is available. Then it will use the Muskingum routing methods for your river routing. Then Penman-Montet equation, Priestley-Taylor equation, Hurgewitz equation, all the three options is available. You can choose any one depending upon your data, what type of data you have. You can choose any method for evapotranspiration computation. Then for sediment computations, it will use modified universal soil loss equation. That universal soil loss equation you might have heard, that each and every parameters represent some kind of a layer, RK, SL, CP. You know? So with the help of that, it will compute the sediment loads. So these are the GIS layers which you have to create before entering into the SWAT environment. Like you have to download these digital elevation models that is available with the help of remote sensing images like SRTM, Aster, Cartosat. Nowadays we are using ALOS Pulsar. They all are available at different resolutions, like 30 meter, 12.5 meters, or SRTM is also available at 90 meter resolutions. That is, I am talking about horizontal resolutions. We have to see the vertical resolutions also while doing that, these types of modeling. Then the second input is your land use land cover maps. As I have mentioned, we have to create again, for land use land cover maps, we have Landsat satellite data, or LIS sensor is also available. Landsat is your US satellite data, or LIS is resource set data that is developed by NRSC. This Indian satellite data is there, resource set. LIS 3, LIS 4 data is also available. LIS 4 data is available at around 5 meter resolution. So if you have not gone through that, so you can go through that or you can download. Then the soil map. If you have some kind of NBSS LUP maps or hard copy maps, you can digitize, you can create your own data. Otherwise, you can use the FAO soil database also. So for this example, I have used FAO soil database, and then again, you have to use the climatic data. If you have station data, that is well and good. If you don't have station data, then you can go for gridded data. AMD is also providing gridded data. Even if we use that GCM data, that is general circulation models or general global climatic models, that is also available at grid. So I'll show you that also. So we have already discussed the climatic data which we require. Then we have also discussed this. So this is the ultimate output of the SWAT output, which we will get in the form of complete water balance equations. We have already discussed. So like I have already told you that after completing that model run and all these things, we have to do some kind of a sensitivity analysis to reduce the number of parameters. So if we are using some kind of a software like SWAT Cup, that is calibration and uncertainty programs, in that particular softwares will get the two types of methods, that global sensitivity analysis or that one at a time sensitivity analysis. So basically in sensitivity analysis, we are trying to identify which parameters are more sensitive to our catchments. Like if, as I have already told, that each and every parameter is having some kind of a range or some kind of a values, like curve number is varying from 0 to 100. Once we are varying with curve number or its value, and then we have to again rerun the model and we have to check the output. If we are getting some different type of output, then that particular parameter would be the sensitive parameters. So it is the nothing means we can say it's a rate of change of output with respect to input. How we are changing that input parameters or how our output is changing with respect to that inputs. So that particular thing is known as your sensitivity analysis. There are two methods, global sensitivity analysis. In that particular methods, what we do, we provide all the parameters. Like if we are talking about discharge parameters like 30-40 parameters, we can give all the parameters, and we use some kind of a statistical method like t-state methods or t-student method or p-state method is there. With the help of that, it will compute. Some optimization techniques is also there. Then it will give what parameters is sensitive to your parameters watershed. Then in one at a time, we have to give one parameter at a time, and we have to rerun the model several times, and then we have to check whether our output is changing or not, depending upon that. So this is the time consuming methods, or global sensitivity analysis is less time consuming as compared to one at a time. It depends. Sensitivity analysis में simulation का कोई role नहीं है. नहीं, वो depend करता है. It depends upon the number of parameters also. You have to give at least 7, 8, 10 parameters. If you are giving 2-3 parameters, then it won't change. At least you have to give 10-20 parameters. Then you will get the that global sensitivity analysis may p test or t state values you will get. You have to increase the number of parameters in single. हाँ, नहीं ऐसा नहीं होगा। हाँ, वो डिपेंड करता है, अगर आपने बहुत सारे इटरेशन ऑलरेडी कर दिए हैं तो फिर चेंज कहाँ से होगा। वो पी फैक्टर आर फैक्टर आपके आता है बेसिकली अनसर्टेनिटी एस्टिमेशंस के लिए, मतलब जो डेटा विच वी आर प्रोवाइडिंग इन ए फॉर्म ऑफ like we have to provide input data means observed data, ठीक है। तो what percentage data 25 PPU प्लॉट्स भी आता है आपके पास, है ना। तो कितना परसेंटेज डेटा वो पर्टिकुलर सॉफ्टवेयर कैप्चर कर रहा है, सारे के सारे आपने लेट्स से 100 पॉइंट्स दिए, 100 पॉइंट्स वो कैप्चर नहीं कर पा रहा है, वो दैट इज द पी वैल्यू एंड आर वैल्यू, ठीक है। इसीलिए अपने को क्या होता है, अगेन पी फैक्टर आर फैक्टर्स भी देखने रहते हैं। सिंस ये इनिशियल स्टेज थी इसलिए मैंने इस पर ज़्यादा फोकस नहीं किया, बट अभी हम मॉडल रन करेंगे तो आई विल शो यू दैट। हाँ बिल्कुल बिल्कुल, अगर आप इस पर ध्यान नहीं दे तो, बट लेकिन स्टैंडर्ड प्रैक्टिस इज देयर, यू शुड लुक इनटू पी फैक्टर आर फैक्टर आल्सो रादर देन आर स्क्वायर एन एस ई। और बेसिकली वी व्हाट वी डू, वी फोकस ऑन आर स्क्वायर एन एस ई ओनली, दैट इज द रॉन्ग प्रैक्टिस। मैं आर श्रीनिवासन सर से मिला हूँ, करीम अब्बास सर से भी मिला हूँ, they are the developer of SWAT, so they also said the same things, because we look p factor and r factor, we don't look r square and SE and pi bias. वो डिपेंड करता है, इफ यू आर रनिंग ऑन डेली स्केल देन 0.5 इज मोर देन सफिशिएंट, यू कैन गो फॉर मीन्स प्रिडिक्शन एंड ऑल दिस थिंग्स। इफ यू आर रनिंग ऑन मंथली स्केल देन 0.6 इज सफिशिएंट, है ना, कोई इशू नहीं। हाँ बिल्कुल, ओवर सिमुलेशन, उसमें ओवर कैलिब्रेशन हो जाता है, सही बात है। तो उस केस में आपको क्या करना है, देन यू हैव टू, आपको क्या करना है, डेटा सेट्स को बाहर लेके आना है। फर्स्ट आपको आइडेंटिफाई करना है विदाउट गोइंग इनटू द स्वेट कैप एंड ऑल दिस थिंग्स, एक्सेल के अंदर ही, कि हाउ योर डेटा इज परफॉर्मिंग ऑब्जर्व वर्सेस सिमुलेटेड, उसमें आर स्क्वायर अभी कितना आ रहा है ना। देन आपको एक पेपर दूंगा मैं अभी, देन यू करीम अब्बास का ही है वो पेपर, है ना, दैट एंटायर यूरोप की उन्होंने वो हाइड्रोलॉजिकल मॉडलिंग करी है, देखा आपने वो पेपर, कॉन्टिनेंटल स्केल हाइड्रोलॉजिकल मॉडलिंग ऑफ द एंटायर यूरोप। इन दैट पर्टिकुलर पेपर दे हैव मेंशंस which they have mentioned some kind of a protocol. If you are getting your observed or simulated values graph, line graph, if you are shifting or your peaks are not matching, then which type of parameters you have to adjust. You don't have to adjust all the 50 parameters. ठीक है, मैं अभी इसमें दिखाई देता हूँ, शायद मेरे पास होगा वो। So if you want, I'll share you this paper. So in that paper they have mentioned a continental scale hydrology and water quality model for Europe. So that was the postdoctorate paper of Karim Abbas sir, they have developed. Yeah. So if you are getting these types of case, then in that case you have to adjust only these parameters. Means this, you have to increase the curve number, you have to decrease the soil available water content, again you have to decrease the soil evaporation compensation factor, groundwater recharge, you have to increase like that. If you are getting these types of pictures, means results, so that is why I am saying, before going to SWAT cup, you have to analyze your data in Excel only. Then you can easily identify which type of parameters you have to adjust. So that is the means best paper which you can refer, or which you can do for calibration and all these things like that. So all the scenarios is given, whether you have to increase the curve number or soil water contents or ESCO, HRU sleep, curve, Manning signs, overland flow and everything. Again, they have also talked about P factor and R factors also in this field. बिल्कुल बिल्कुल नहीं, ये दैट इज़ द वन ऑफ द लिमिटेशंस ऑफ स्वेट के पीक इसमें थोड़ा मैच नहीं करता है। ऑब्वियसली ऑब्वियसली एनएस वैल्यू वो डिस्चार्ज की उस पर ही डिपेंड करता है ज़्यादातर। हाँ 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 हाँ, उस केस में फिर हम क्या करते हैं, ओवर कैलिब्रेशन करने लग जाता है। अदरवाइज आप अगर डेली स्केल पे कर रहे हैं, इफ़ यू आर गेटिंग 0.6 दैट इज़ मोर देन सफिशिएंट। मंथली स्केल में 0.65 0.7 भी है तो मोर देन सफिशिएंट है। हाँ, पूरा ये टेबल है, ये अभी आपके ये मैं बता रहा था, ये दिस इज द टेबल विच इज़ गिवन बाय मोरेशी इट ऑल। ठीक है, इफ़ यू आर गेटिंग आर स्क्वायर एंड एस ई पी बाइस वैल्यू विद इन दैट रेंज देन ओनली योर मॉडल विल बी satisfactory। ये this is values are given for discharge. For sediment these are at some upper side, and they have increases some kind of a p-bias values for sediment also, because calibration of sediment is not a easy task. Okay, so these are the statics which we are interested. Other than these statics, some BR square or some other parameter is also there. Culling-Gupta efficiency, some other parameters is also there. So now, if we talk about that application of SWAT, so we can determine the hydrology as we have already discussed. We can compute the transportation, sediment transportation, nutrient, pesticide. We can do the water quality analysis also, like phosphorus, nutrient, all these things we can do. Then we can do some kind of a climate change analysis, even land use land cover change analysis. If you have temporal data of your study area, how land use changes are taking place, you can incorporate these changes in your model, or the climatic data if you have, so you can incorporate these data also. So as I have mentioned that data sources, so 4 types of data is required, 5 types of data. So from where you can get, so I think you all know, you can get the DM data from Bhunidhi portals. Bhuvan portal is not working nowadays, so Bhunidhi portal is there. From there you can get the Cartoset data as well as the list 4 data. Even sentinel data you can get at 10 or 20 meters, or list 4 data you can get at 5 meter resolutions, or you will get the Cartoset data. For SRTM or ASTA data you have to use USGS. They will provide the GeoTIFF format, raster data format data. So that becomes the input for your SWAT model. So first you have to create login and all this thing. The second portal is USGS. From here you will get the SRTM data or ASTA data, digital elevation data, as well as the Landsat data. Landsat data that is starting from 1975 to till today. From Landsat 1 to Landsat 9 data is presently running. You will get all these data sets. If you do some kind of a land use land cover change analysis, you can do. Then that Landsat data is available at 30 meter resolutions. If you want some kind of a fine resolution data, you can go for Sentinel data that is available at 10 meters. Okay, that from Alaska satellite web portals. So these types of inputs we have already discussed. Then if you don't want to create your own land use map, then ISRI has provided Sentinel-2 data at 10 meter. They have directly give you the land use land cover maps for the entire world. Okay, then other sources is also there. Global irrigated area maps is there. Moody's land cover maps is there, but they are available at very coarse resolution. So better you can use that Sentinel data that is provided by ISRI. Then even Bhuvan also you will get some kind of a classified maps, but that is in the form of JPEG image. You have to geo-reference that images. They are not geo-referenced, so you can't readily use that data. So now this is the, yeah. So if you want to download that ISRI data, you will get window like that. From that window you have to download the data. 2017 to 2024 data is available for the complete world at 10 meter resolution. They have classified maps, land use land cover maps you can directly get. Then other maps is also there. Global irrigated area maps that is available around 5 meter resolutions. Then those who want to do some kind of a temporal analysis, they can follow this link, or from that you will get the 1985, 1995, 2005 data sets for the complete India. Okay, that is made on Landsat data. Then Moody's data is also available. So like that you can create your own land use land cover map with the help of Landsat or Sentinel data. So these are some examples. Then from FAO you can get the soil map, or the alternate is this National Bureau of Soil Survey and Land Use Planning maps. From this you can get the soil maps. So this is the link for your soil map. You will get the download options here. So along the data you will get the raster file as well as the database. So while doing some kind of a modelings, you have to integrate that database with your raster image. Okay, so you should know some basics of GIS also. If you want to digitize some kind of a watershed boundary and all these things, so Survey of India is also providing topo sheets. Just you have to register on that Survey of India portals, and you can download the topo sheets of your study area for your land use land cover accuracy assessment. This is the FAO map, and this is the map which I have created from NBSS LUP maps. So you can clearly see in FAO I was getting only 4 soil classes, while in NBSS LUP around 50 classes I was getting. Okay, and then I have also created the database in Excel, and then I have merged that database with that raster, because both Excel database as well as the raster image is required in SWAT modeling. Then the climatic data you can get from IMD. Then global weather data is also available from SWAT website. Or if you are interested in CMF 5 data or CMF 6 data, you can go for web portal is developed by Professor Vimal Mishra, if you might have heard. Professor Vimal Mishra from IIT Gandhinagar, they have developed a web portal for all the Indian river basins, in which they have provided the SSP scenarios data. CMF 5 data would give you the RCP scenario, reconcentration pathway scenarios. Okay, and now the research community is using you might have heard about in IPCC lectures, that CMF 6 data is currently we are using. They are providing SSP, socio-economic pathway scenarios. So just you refer that paper. You all know that you can get the IMD data from IMD websites. They are providing rainfall data, daily rainfall data at 0.25 degree by 0.25 degree net CDF files. You have to convert that net CDF file into CSV format and all these things. I'll show you how to what type of format is required in SWAT. Then global weather data from SWAT website, you can download that data. Then for CMF 6 data, you just go through this paper. In this paper, they have provided the link. Following that links, you will get the complete data, CMF 6 data for your entire Indian river basins. Like I have downloaded for my study area. So there are around 13 SSP scenarios, 13 GCMs data is available for different SSP scenarios. Historical data is also there, then future climatic data is also there. From 2011 to till the end of the century, 2100, they have provided all this data for the entire river basins. 13 models, 13 GCMs data is there. Maybe data bhi show karta tha. Yeah, they have already did that bias correction and everything, so you can directly use it. First you have to match once. You have to cite their paper, or you have to acknowledge. Yeah, you have to just give that reference from their paper also. So for our study, which I'll show you, we have used only 5 GCM data, and that is most suitable for Indian regions, and that is that conclusion is given by Suvimal Ghosh, Professor Suvimal Ghosh. Based on that papers, we have chosen 5 climatic data only. Yeah. Yeah, you can choose. Yeah, you can choose all the 13 models, or even some models are not performing well, you can omit that models. Yeah, that is the basic criteria you can use. So then, if you want to directly use the SWAT models, so from that particular source, you can get the entire India data sets for the complete India in the SWAT format only. the land use maps, soil maps, everything you will get in the SWOT formats. And then for that you require some kind of observed data. So water resource information systems, that is known as your India Varis systems, is there. I think they are updating their websites. So nowadays you might not be able to download some kind of observed data. Otherwise, for classified river basins, you will get all the data. Classified means that are not sharing the international boundaries. India has divided their river basins into two systems, classified and non-classified. That Ganga, Indus, and all this, which Brahmaputra, they are sharing international boundaries, so it is difficult to get that data. But otherwise, for southern Indian regions like Tapi, Narmada, Krishna, Godavari, you will get all this data on India Varis websites. So this is the portals from which you can get the data. So once you have identify the models, you have collected some kind of input data, you have prepared the inputs, everything is ready, or you have done models, you have done calibration and all these things. Now you are ready for scenario generation. Okay, so till now with what we have done, we have created some kind of a base model with the help of historical data. Historical data means we have used DM data, we have used IMD data. Till today we have available whatever data from 19012 2024 and all these things. And then we have completed the calibration and all these things. Once we have satisfied with our models, we can use the GCM data with our calibrated models. So for this particular study, we have used 5 GCM data that is being given us to that regional climatic projections in India with a statistical downscaling. This is the portals from which you can download the CMIP 5 data. They are providing RCP 4.5 or RCP 8.5 data. For 5 GCM data they are providing. I'll show you that 5 GCM. And then we have used the readily available NRSC land use land cover map that is available at 56 meter resolutions. We have created that NBSS LUP soil map. We have used 30 meter DM data, and the resolutions of GCM data was 0.25 degree by 0.25 degree. Then we have used the observed discharge data. So this is the GIS representations of my study area. Like that we have created. Okay. Then we have done all kind of simulations on all these things at daily scales. We have created at 2 stations was there, gauging station. One is Burhanpur, second one is your Hatnur. Hatnur was our dam. So whatever inflow we are getting, we have to provide as a outflow to some other catchment area also. So like that we have computed at daily scales. These are the P factor, R factor values which we are talking about. And then this percentage statistics we have also computed. We have computed that basin scale values. All we'll do in that next tutorial part also. So this is the basic picture which we got in the form of that water balance equations, and these are the different models which we have used. That is BNU and CCMA, that is Beijing National University model, and the second one is Canadian model, and the third one is German model, that is Max Planck Institute lower resolutions models. So these 5 models for 2 different scenarios, RCP scenario, reconcentration pathway scenario is there, that is based on the carbon emissions. That 4.5 is the scenario, is the moderate scenario, 8.5 is the worst scenario. So we have got these types of complete hydrology. So what we have concluded in this study, that actually I am not showing all the results because we are under review. My paper, one of my paper is under review, so I am not able to show complete results of these things. So basically that pattern is changing, rainfall patterns. We are getting the same rainfall amount within the catchment, but the rainfall pattern is shifting. We are not getting in monsoon months, we are getting in non-monsoon months. The amount is rainfall is the same. So that shifting pattern is taking place, not only within our basin, in some other catchments also within India also. So like that we have we have divided the entire data sets into near futures, mid futures and far futures. So we have computed all this rainfall, surface runoff, water yield, ET, we have computed. And then once you are using some kind of a 3-4 types of GCM models and all these things, then for reaching at a particular conclusions, you require some kind of a averaging types of techniques. That averaging techniques is known as your ensembling of GCMs. So in that ensembling techniques, you combines the results of 4, 5, whatever GCMs we are using. So in my case, I simply use the mean average of all the 5 models, and I have compared that average with the historical data for both the cases, RCP 4.5 and 8.5 scenarios. So we have also computed that flow duration curves and flood frequency analysis. We have done everything we have done, and we have concluded that some kind of a rainfall shifting, as well as that evapotranspiration is also increasing in our basins, and then land use change is also taking place. So in my study area, that is the Tapi basins, initially it was 50% of area is covered by forested area. Now what we have concluded till the end of this 2020 land use maps, around 20% forested area has been reduced, and they have converted into agricultural land. So significant hydrological changes has been occurring in these basins. So like that, you can do some kind of a hydrological modelings or climate change studies. Similarly, if you have land use cover maps, like from 1970 or 85, 95, like that, temporal land use maps, you can also incorporate these maps in SWAT models. So in tutorial exercise, we'll see. I'll provide you the readily available data, that land use, soil map, everything. So you just try to run the model so that you will get the confidence. Or otherwise, what you can do, I have shown you that one India dataset portal on SWAT website. You can directly go to that, or you can download the data for your study area. So yesterday I have shared that link related to softwares. So if you have downloaded that QGIS and all these things, that is very good. Otherwise you can download, or you just visit the SWAT website. Those who are not visited or not gone through that website, please go through that website. Everything you will get, whatever software you want, you will get. If you are working on ArcGIS, if you have licensed versions, you can go to the software folders. You will get SWAT Plus is the latest versions which they are using, or SWAT 2012 is the older versions. And then here you will get different types of SWAT Cup Plus folders, QGIS, everything you will get. Then some kind of a data set is also available, like as I've said, that India data sets for SWAT 2012. If you simply just click on that, you will get that portals which I have shown you. You can download for the entire data set, entire India. You will get the DM, entire India. You will get the land use map, soil map, even weather data. Because it is very difficult to download that NAT-CDF file and that to convert NAT-CDF file into the SWAT format, because SWAT required the data in the form of text. It requires data in the raster format as well as in the text format. So you have to create the data. I'm just showing you. How you have to create the data. So like that, first I show you the weather data. You have, if you have basin means station data, then you have to create the text file for individual station. Or if you are using grid data for individual grid, you have to create a single text file like that. The first row would mention the year 2001, 01 is the month, 01 is the date, 1st January 2001 will read like that. And then the data start. Wherever it will stops, that would be the ending year, month or day of your data sets. Like that. If I have data from 2001 to 2020, so the last day means data would represent the last date of the complete data sets. Okay, so like that we have to create for rainfall data as well as the temperature data. You have to create like that. So this is the maximum temperature data separated by comma, minimum temperature data of the day. daily data you required. So like that you have to create single files for each stations or each grid. Then you have to create a master file. In that file you have to mention only the stations ID, their lat long values. If you have elevation, then you can mention the elevation, otherwise you can keep 00, or you can do whatever means points you have, just overlay on your DM data, or you can extract the elevation values, or you can give this. So these types of text files you have to create for your temperature data as well as the precipitation data. So while running the models, we have to provide this file. From these files, it will automatically fetch all this data from this particular folder for each grid or for each station's data. So this is the format of your temperature data. Along with temperature data, you need some kind of a soil data or land use data. So soil data you required in the raster format that would be created in your GIS software. And then along with soil data or land use data, you require some kind of a CSV file that is in SWAT, that is known as your lookup table. That lookup table would contain the raster images, then the SWAT code, that 4-digit code would be there that represents the land use class, like WATR would represent the water class, FRST represent the forest class, AGRL represent the agriculture class, URBN represent the urban class, BARR represent the barren land, RNG represent the range land, like that you have to give. And from that particular code, it will fetch the information in the SWAT database. Once you download that SWAT software, QSWAT software, you will get the reference database folder. QSWAT reference 2012 for .mdb format file is there. From that files, it will connect the particular land use informations. Okay, so like that, you have to create a soil database also. So raster format image is there. Along with that raster image, you have to create one lookup table for soil database also. So these are the code which is being used in your soil database. Since I am using the FAO soil database, so FAO soil database is by default provided in your QSWAT reference database. If you are creating your own data sets, then you have to update your user soil file in your reference database. You have to paste all this data, or you have to copy all this data, whatever you have created soil database, in your reference database. Otherwise, it won't be able to run the models. Okay, if you have reservoir information, then also you can incorporate reservoir information. What are the volume of the reservoir, what are the spillway level or maximum spillway, minimum spillway levels, what are the number of gates, what types of management practices is taking place, every types of things we can do. So okay, we'll take tea break here, or after tea we'll start the exercise. So meanwhile, those who did not download or install the QGIS software, please install the QGIS software. I have already shared the link. Just you have to download the QGIS 3.4 versions from that Google Drive. Don't download the SWAT Plus. वो आपके लिए नहीं है ना. Just I have also shared the QSWAT version 2.1.0. Install that QSWAT, QGIS, SWAT editor, SWAT check. Okay. Then after tea, we'll start the hands-on exercise. WhatsApp group. Please download that folder.
So we can start now.
Yeah, we will tell. Then we will start.
It's good.
Please, you start.
Oh, you can be here. All right, good afternoon. We'll start again. All right, I heard you already learned everything about hydrological modeling, right? So right now is the time to do some hands-on exercise. So I'm sure, yeah, you already talked about the SWAP model, the background. So it's one of the widely used hydrological model, right? So it's semi-distributed. So it's a water basin-based model, and some parameters are lumped parameters. Some are like a basin-specific. So it's it was originally developed by USDA in the United States. One of the original developers is actually from India originally, right? So he actually one of the key players in the SWAP model. So the U.S. government has been actually widely promotes the use of this model for different purposes, right? So because this model is called soil water assessment tool, right? So water and soil both are important. So this model actually has been used for predicting like sediment and water quality, right? Besides just water quantity. So that's why you can use this model to assess land use change, climate change, how different things impact water process. So it's very useful tool. So I guess it's a good chance you guys have a chance to like play with it and see what happens, right? So actually there are training workshops like as an international level, national level, but yeah, I guess but here is more. Yeah, I guess a condensed version you can play with it. So, yeah, I guess Dr. Priya Midra is an expert on SWAP for many years since PhD, and yeah, he knows everything about SWAP, and he will be the main person actually working with you on the hands-on exercise. So I guess I'll give this to you then.
Thank you,
Yeah.
Professor Ling. Okay, yeah, thank you. So now we'll start that particularly exercise related to SWAT. So for that, I have already shared that QGIS software. I think all of you have downloaded that software, and QSWAT software you have already downloaded. Now recently I have shared one folder, that is input data folder, that is containing all the data which is required for SWAT model. So in that particular folder, we have 4 subfolder. That is DM, input data folder containing the 4 folder. That a DM folder is there, LULC folder is there, soil folder is there, weather data folder is there, and output folder is there. Okay, so we'll directly switch on to the software and we'll start the QGIS. So I am using the bit older version of QGIS, and your is QGIS 3.4. So if you have downloaded that QGIS software, so simply just click on that QGIS desktop. Simply click on that QGIS desktop icon. All of you getting that QGIS desktop icon? Just simply click, or click gently. Do not click multiple times. It's a open source software. Your computer will be hanged. So click 1 or 2 times only. So for your, that would show the QGIS 3.4. Okay, you have downloaded that SWAT editor also, SWAT check, everything. If you didn't download that SWAT editor or SWAT check, then you would not get results related to SWAT output. now this type of window will open. In your case, you have to click on that empty map. Okay. You are getting this type of window. This is the main QGIS window, map window is there. This is the layer panel in which all the layer which we are working would be displayed here. All of you getting this window? Okay. So here you will get the icon of SWAT. Are you getting this icon? That SWAT icon? If you are not getting that icon, then you just go to the plugins, go to manage and install plugin. Just click on manage and install plugin. Those who are not getting that particular SWAT icon, QSWAT icon. Click on manage and install plugins. Here just go to the installed plugins. You will get this type of icon, QSWAT. You have to just check on this box. As soon as you check on this box, that particular icon would be appear in your menu bar. All of you getting this? Those who didn't get? Anybody? Okay. So then you have to click on that particular SWAT, QSWAT icon. So this type of dialog box will be open. It will shows the new project, existing project, and the about the informations. If you click on that about, you will get the QSWAT version. So I am using the QSWAT version 2.4, that QSWAT version 1.3 with QGIS version 2.4, and in your case it would be QSWAT version 2.0. And what is the QGIS version? 3.14. Okay, all of you getting this type of window? So if you are starting a new projects, we'll click on new projects. If you have already built some kind of projects, you can go for existing projects. Since we are starting a new project, so we'll go for new projects. Simply click on new project. It will ask to save that particular projects. So wherever you want, you can save in a particular directory. Don't save in C directory. Save in E directory or D drive or any other drive. Don't save in C drive. Okay. So just click, just give the name project. Simply, and it will save the files in the QGIS format. Okay, all of you getting this window? Just simply click save. As soon as you click the save button, the dialog box, it will show the 3 steps. Initially the steps were not appearing in this window. Now it is showing the steps. All of you getting this? Now it is showing the steps. So if we see, the step 1 is highlighted, step 2 and step 3 are enabled. So the step first is delineate watershed. Okay. So once we completed that delineate watershed options, then only option second would appear. Once we complete the second step second, then we'll go for third option, step third. After completing the and running the SWOT model, step 4 will appear. Till now we are getting only 3 steps. All of you getting this? So before going to that delineate watershed, just I want to show you the input data which I have shared you. You please unzip that folder, whatever I shared with you, that input data folder, that is containing 5 subfolder. The first one is related to DM, in which I have kept the SRTM DM at 30-meter resolutions. Then the second is land use land cover map of mine study area, then with lookup table. Then the observed data points is also there. I think in yours also some observed data is also there that would require during the calibration. Then the outlet point is there. I have kept 2 shape files. one is projected, one is in geographic coordinate systems. Okay, that output 2 is projected coordinate systems. We'll use the projected coordinate systems. So whenever you do some kind of a SWOT modelings, keep in mind that all the data should be in a projected coordinate systems. Okay, whenever we work in GIS, so there are two coordinate systems. One is geographic coordinate systems, that is used like you might have heard about WGS 1984. That is WGS 1984 is a geographic coordinate system that represents that is angular measurements that represents the values in latitude longitude systems, but that won't be able to measure the area and parameters. For that we have to convert into Cartesian coordinate systems, XY coordinate systems. So we have to project our data sets, our raster data sets in projected coordinate systems. So most of the times we use that UTM, Universal Transfer Mercator systems. So all the data is projected in UTM zone 43 and node systems. You might have heard about these things. And then similarly we have soil data with lookup tables, then the weather data. That weather data is containing two folders. I have kept rainfall data in separate folder and temperature data in separate folder. In that rainfall data, it is having all the station data along with some shapefile is also is there. With GIS shapefile is also there. If you want to open that shapefiles, you can get the spatial distributions of your rainfall data. And then one file is also there, PCB files, that would be required during when we give that weather data. So we'll provide that file, PCB file, that is containing the information of your latitude, longitude and all the station names with elevations. So we'll provide that file. According to that files, it will fetch all the informations of your individual weather stations data. Okay, so all of you with me, you are here. So now just simply click on step 1, that is your delineate watershed. You will get the window like this. Okay. Yeah. That QSWAT. So just go to that plugins. Okay, you have downloaded that QSWAT. You downloaded. Still it is not coming. Huh? Yeah, I am just saying, just go to that plugins, manage and install plugins, go to installed and that check that QSWAT. It is showing QSWAT. Check it. And now it is showing. Okay, let me check. Okay. So this window will appear. In that particular window, you will get the option of select DM, that is digital elevation model. We have to select, and then it will show the delineate watershed, use existing watershed boundary, DM properties, tau DM. So if you have means existing watershed boundary, we can use the existing watershed boundary. We can also give the shapefile of that watershed boundary, and then whatever dam properties you are having, it will show once we select that particular DM. So just click on that select button and go to the input data folder, the DM folder. In that DM folder, you have to select the TIFF file, dm.tiff file. It will show the type of the file. Different files will be shared. इसको ये बंद कर दी प्रज्ञा. Switch off that fan. Just select the TIFF file of DM and click open. In background, the DM will be open. Now it is showing all the properties, in which coordinate systems is there, what are the latitude longitude system is there, everything say. Cell size is also there. I am using the 30 meter by 30 meter DM, so it is showing the 29.55 meter by 29.55 meter DM. So then tau DM option is presently it is not showing anything. That is the terrain analysis using digital elevation model. So once we'll create some kind of a stream network and we'll give the command of watershed, then it will run. Okay. So now we'll come to the delineate watershed options. Here you will get the threshold value, define threshold values. In the background it will showing like that. All of you getting this DM? Huh? Just simply you have to select the TIFF file, otherwise it won't open. TIFF format. Again I am showing you. You select that DM with that symbol. Okay. Then only it will appear. Don't select any other file format. Now it is appearing. Everyone is getting the DM with hillshade. So here we have to define some kind of a threshold. This is the threshold which we have to use for generation of stream network. So what are the number of cells values which they are going to contribute to in the stream network which we have to provide. We can provide in the number of cells also, or we can provide in the form of area. So since we are using 30 meter resolution DM, if we use smaller thresholds, it will create more number of streams and it will take too much time. So what we can do to reduce the times or to eliminate some we can say arbitrary streams, we can increase the threshold value. So we'll get the main streams only. So I'll just use the threshold as a 600 square kilometer. If we drop down this, you will get the different units, hectares, meters, or miles, acres, square feet also. So we'll use that square kilometers. And then one option is there, create streams. Okay. So just select the 600 square kilometer. It will automatically change the number of cells values, and just simply click on create streams. So simply gently click, only one click. So once you click, the moment you click that create streams, it will start that fill DM, that flow direction it will compute, flow accumulation it will compute, then tau DM will start taking place. Okay, all of you getting this? And don't click multiple times. Okay, since we are using 30 meter DM, so it will take 5-10 minutes, or depending upon your computer, whatever RAM you are using, so accordingly it will take time. The study area which I have chosen is part of that Bisalpur catchment area, that is in Rajasthan. So anybody got that stream network or still running? Did you get that stream network? So if you are using 90 meter DM data, then the processing time would be fast. So once you will get that stream network, after that we have to select the outlet location. So for that I have provided outlet point locations. So we have to import that point locations, and then we have to draw manually that outlet locations. Then we have to select that locations. Then we'll create the watershed. Yeah, that area is Bisalpur catchment area is there. That is in Rajasthan. So Banas river is there. Yeah, complete flat. Here we have that dam. will provide the outlet here. If you zoom in that particular DM, you will get the feel. Yeah. So how many of you got that stream network? Okay, those who have got that stream network, just click on that vector. Oh no, not on vector, that click on layers, add layer, add vector layer. Just click on layer. In that layer part you will get the add layer option, add vector layer. Just click on that add vector layer and then select the output which I have provided in the output folder file. Just select the output file in the output folder. Okay, then the output location will be displayed in your stream network. Just select the output to file, output to SHP file. One second. Yeah, .shp format you have to select. Let me show you. एक मिनट मैं शो करता हूँ अभी. Wait, it will show. Just click on layers, add layer, add vector layer, then you have to select the I am showing you .shp format only. In that outlet folder, you have to select the yeah. Okay, no problem. You can select that SHX format also. The last one. Okay. Just click open. It will show like that. Now it is showing .shx format you can select. If SHP is not showing, you can select the SHX format. Okay, now it is showing. हाँ स्ट्रीम के ऊपर नहीं है, इंटेंशनली नहीं है है ना, क्योंकि बिकॉज वी हैव टू ड्रॉ ऑन स्ट्रीम्स एंड वी हैव टू स्नैप दैट, समटाइम्स इट हैपन्स, ये मोस्ट ऑफ द टाइम्स स्टूडेंट्स डू सच टाइप ऑफ मिस्टेक्स, दैट इज वाई विल डू दैट इनलेट आउटलेट, ड्रॉ इनलेट आउटलेट ऑप्शंस विल यूज. ओके, बिल्कुल ऑब्वियसली, so it will take more times, so that is why I have kept 600 kilometer square. So you are not getting that stream network is not getting, or some So what we can do, we'll just zoom into that layer. No. Just zoom into that layer. Okay. And we have one option here, draw inlet outlet options. Just click on that. Okay. So in your case, you will get like this window: outlet, reservoir, inlet, point source. Okay. So just click on the river, just streams, the ending point of the streams. Just click on that. No, why it is going to dam? Dams ना, just stream के ऊपर जो stream network आपको मिला है ना, just you have to select on that stream network, otherwise it won't create the watershed. Just make sure that you are clicking on the streams just above the streams, so that it will means completely overlay on the streams. Yeah, just you check whether means whatever threshold you are taking accordingly, उसके according आएगा, वो देखिए आप उस पे. Just click on that and then you will get this options: outlet, reservoir, inlet and point source. So we are defining right now the outlet of the basin. Okay, so simply click on OK. Then you will get that select inlet outlet options. ठीक है. So one message would be appear. In that message it is showing that you have to select the outlet, whatever outlet you have selected you have to select, and press the control button and hold if you have multiple output buttons. Okay, like that you have to select, its color will change and it will turn yellow. Okay, then simply click on save button. Once you have select that, it will shows that one inlet outlet or outlet point is selected. If you are sure that whatever outlet point is you have selected is completely lying on the streams, then no need to go for review snap. Or if you are not sure, then you can go for review snap. Okay, snap means, let's see, the point which I have selected is not lying on that streams, so I'll go for review snap. So for that I have specified the threshold length for the review snap. एक सेकंड में ये कर लेता हूँ, फिर आते हैं ना. Once you have click on review snap, it will by default snap the outlet point on the stream network itself. Once you complete this, just click on create watershed. It will create the watershed. Again, it will take time. Second. So this type of watershed you will get. This type of watershed you get once you do that snap watershed and all these things. Take over. So once you get that particular watersheds, if you have defined that lower threshold value, you will get many sub watersheds. If you want to merge that particular watersheds, the options will be here. You can merge a smaller watershed into a bigger watershed. Right now we are not going to use that merge options. And then you have to define if some reservoir operations, if you want to do, you can select a reservoir operations here. Since we have dam here, so we can select as a reservoir watershed. Or once we are defining that outlet, we are getting some kind of a outlet, reservoir options, inlet options is there, and some point source information is there. So for outlet, we have defined the outlet. For inlet, if you are getting some source of water from the other rivers, so in that case we can define the inlet at the junctions of two river points. So one is coming from upper sides and one from other sides, so we can define the inlet points also. If we have reservoirs, so we can define the reservoirs also during that times only, where we have defined the outlet point in that times only. So once we have done this, just simply click on add point source. Here we are not selecting any reservoir sub-basins also. Simply we are clicking the add point source and then click OK. So it will give some kind of a numbers to the watersheds. Watershed 1, 2, 3. So 3 sub watersheds we have created. And then add point source. Then the step 1 would be done and the step 2 is enable. It will show in your SWAT folder, is QSWAT icon. Okay. For your case, that visualize is not visible in your case because I am using that already running model, existing project. So just simply click on create HRUs. Okay. So from that create HRUs, you will get this type of window. In that window, we have to select land use map, soil map along with lookup tables. So here first you have to select the use CSV file. Just click on that drop down land use table. So in that table format we have to select use CSV. Similarly for soil we have to select the use CSV file. Okay. In your case that particular tab would be the blank, and then here we have to define the slope classes. So we can define 0 to 5% one class of the slope, 5 to 10% would be the another class of the slope, and then greater than 10%. So I have divided into 3 classes the slope variations. Then you have to click on that select land use map. So again go to the input data folder, then LULC folder is there. And from that LULC you have to select again TIFF file. These types of different format you will get. From that you have to select the TIFF format only. Select the TIFF LULC file. Then go for soil map, select soil map. And then select the soil.tiff file. So if you are not getting that create HRU options, then you just simply drag it from that corner, it will show. Soil map dot tiff file. For both LULC and soil, for both the files you have to select the TIFF file format only. Okay. Then here you will get the soil database format. Since we are working on our data, so we will use the user soil. If you are using that state go or SSURG soil database format that is developed by USGS and Texas University and all these things. So you can, if you have those database, you can choose that database also. Then we have to read just click on read button. So it will ask the choose land use lookup table. That message we have to read, choose land use lookup CSV file. So go into the input data folder. I have already provided you the lookup table with land use, which I have shown you. Just select the land use lookup table. Then it will ask the soil lookup table. Then go to the input data folder, soil. Then you have to select the soil lookup table. All of you have selected all the land use map, soil lookup, everything. किस में आ रहा है? एक सेकंड, लेट मी चेक. give that information of land use and soils also. How your catchment area is divided into different land use classes. So once your create HRU options will be done, then your step second is done, step 3 would be enabled. That वो मेरा आ रहा आपके नहीं आएगा ना, एक्चुअली वो मेरा अभी जो उसमें टाइम ज़्यादा आ रहा था तो जो मेरे पास पहले से रन था उसमें है ना. So just click on edit inputs and run SWAT. So it will ask to connect to database. Just click on that, connect to database. All the options related to SWAT editor will be enabled. That whether input files, edit, SWAT input, SWAT simulations, all these things. All of you getting this? In that, go to that SWAT executables. That executable file will get that SWAT editor. Go to SWAT website, SWAT executables. Just click on then. Go to that SWAT editor and then download SWAT editor. Just download it and install it. Everyone, you installed that SWAT editor? इंस्टॉल हो गया, ज़्यादा टाइम नहीं लगेगा उसमें. All of you have downloaded that SWAT editor. Just install that SWAT editor. आपका हुआ? कोई बात नहीं, अभी ये रेक्टिफाई कर लीजिए वरना फिर वहाँ जाने के बाद नहीं होगी. वो दिखा रहा है एरर. एक सेकंड है ना, मैं शेयर करता हूँ .NET फ्रेमवर्क के लिए भी. 1 मिनट, वो डाउनलोड कर लीजिए फाइल. Those who are getting such type of errors, I am sharing all the files and please try to install that file. Otherwise it will be very big trouble for you. मतलब आपके लिए पॉसिबल नहीं हो पाएगा वो करना. ठीक है. Yeah. Those who are getting .NET file errors, just download that file or install it. So everyone that installed that SWAT editor, now it's working. You got this window, edit input and run SWAT. We are just one step behind to run the SWAT model. So how many of you have downloaded that SWAT editor? Install that. Now you are getting that edit, run and SWAT output. Huh? .NET wala problem. Just I have shared that .NET file. You download that file and install it. I have shared on WhatsApp. You just download that .NET file also. Otherwise, what happened now, from going from this place, you won't be able to identify these types of error, or even .NET files comes in different versions. It would be very difficult to identify particular versions. That is why I am sharing that version which is compatible to that QGIS and QSWAT version. Yeah. .NET framework files is available in different formats also. Yeah, that is the main issue. So you just download that .NET framework file and install it. So it won't give that error. Then you will be able to compute. So how many of you getting this type of dialog box? Connect to database. आ गया आपके? हो गया रन? आपके? उसके बाद आप क्लिक करिए वो ऑटोमेटिक वो डाउनलोड होना स्टार्ट हो जाएगा. So how many of you getting this? So okay. So just click on connect to database. Database connections successful. You will get this message. Okay. Just see the steps. I'll share you one PDF in which I have all the screenshots related to that with the description of the SWAT output files. I'm just show you. Yeah. So I have all this file with steps. Everything is written. You just follow all these steps. Okay. So you'll get everything here. So don't worry. Just follow me. If you are not able to do, you can do at your room or home also. No issue. Okay, let me complete this. So then we have to provide the weather information. Till now what we have done, we have provided the digital elevation model. From that it has computed the slope as well as the watershed and sub watershed. We have provided the land use information, we have provided the soil informations, and then the SWAT model performed the overlay analysis. Based on the overlay analysis, it has created the HRUs, raster overlay analysis it has performed. Then it has created the HRUs, hydrological response unit, and then we have to provide the climate data, weather data. Then for here that we have right input tables from weather stations, we have to give the climatic data. For that we'll get this types of dialog box related to rainfall data, temperature data, wind speed data, solar radiation, relative humidity. Then one option is there, weather generated data. So what happens once we providing some kind of a rainfall data? So if we are using some kind of a station data, so we'll get some missing rainfall data also. But with the help of that weather generator files, it will create the runoff for those days where we don't have the rainfall or we have missing rainfall data. For that missing rainfall data, we have to provide -99 notations for that SWAT format. We don't provide 0. Because it assumes 0 as a data, means value, some kind of a value. It runs, it assumes -99 as a no data things. So with the help of that weather generator, if you have some kind of a statistics, you can generate. Just visit that SWAT websites, you will get the stand-alone software for that weather generator. You can create your own weather generator file. If you don't have your own, you can simply select by default whatever we are getting in the software. So here we provide the rainfall informations. As I have already mentioned, just select. So you will get two types of options, simulation or rain gauges. So since we have our own measured data that from the rain gauge stations, so we'll select the rain gauge. Then it will ask the precipitation time steps. We have the daily data. If you have hourly data, then you can select the sub daily options also is there. So since we are dealing on daily data, so we'll select the daily data. Then it will ask the location tables. In location tables, we'll provide the PCP text files, which I have shown you, that is containing the station's name, latitude, longitude, and elevation informations. So simply just click on that, browse that particular path where we have saved that location, input data, weather data, rainfall data. These are the rain gauge stations within our study area, and we'll select the PCB files in which I have shown you that latitude, longitude information is there. Simply click OK. Similarly, select temperature data. For temperature data also, again we'll select the climate stations. Then select the location table. We have to select the location table. From temperature again, we'll select the location table. If you have wind speed, solar radiations, or relative humidity data, then again you have to select the gauges, then you can go. Otherwise, you can go for simulations. Then we'll select the weather generator. For weather generator, if you have created your weather generator files, then we can select the weather generator user file. In that user file, that is by default file in QSWAT reference database. We have to update that file. Otherwise, by default, it will select it and it will give the 4 station counts. Some statistics have been generated based on that. Then simply click OK. Now here we are providing the weather data. So invalid. Okay, because of the nomenclatures and the folders name, sometimes we are getting these types of error. And don't give the name related to SWAT or GIS and all these things. They also create some kind of a trouble to systems. Don't give dot and then space unnecessary. Otherwise, every time you will get that error. थोड़ा सा पहले रन करा हुआ था मेरा ये. नहीं, ऐसे तो मैंने रन कर रखा है उसको कितनी बार भी. हाँ, पहले रन हुआ है ये. यही दिक्कत है. एक्चुअली क्या है ना, इसने एक सेकंड. Okay. Okay, don't worry if we are not getting this. Okay, so once we have given that out, rainfall data and all these things, we'll get this type of window. It will create all the input files. Okay, let me check what happened with me after completing this. I'll show you. Then we have to go to that SWAT simulations. There we'll get that run SWAT models. So once we click on that run SWAT model, we'll get this type of window. Or here, that starting and ending range will be shown depending upon the rainfall or weather data, whatever you are getting. So then you will get the three options: daily, yearly or monthly. From that we have to select what type of output we want: daily output, monthly output or yearly output, with NY skip informations we have to provide to stabilize the initial model conditions. So we are providing that 3 years, 5 years we can provide. For those 3 years, 5 years, the model won't give the print the output, or it will compute the output as we are giving that starting date is 90. So from 94 onwards, it will print the output. Then we'll go to that setup SWAT model, setup SWAT run, and then run SWAT. So this type of window will appear, and then our model will be run. Once we'll get that, we'll get the successful model run output. And then we'll go for SWAT check output. Here, this type of window we'll get, and we have to examine model output. From that we can get this type of basin hydrology or the complete hydrological cycle for our basin. Okay, so all this graphical output would be stored in the text format also. So in that SWAT folder is there, one folder is there, text in output folder. So in that folders you will get all this information. So all the output would be saved in your scenario folder, in default folder, text in out folder. So once you have done calibrations, or you have to take all these files in SWAT cup. So SWAT cup copy all these files and then do alterations, whatever calibration or you are adjusting the parameters, all the alteration would be done in these files. So these files would be taken in the SWAT cups. And again, once you satisfied with your calibration, you have to bring these files in this folder again for doing that climate change analysis and all these things. Then you have to go to edit SWAT input, and you have to provide the rainfall data and temperature data for your future, and then you have to rerun. Yeah, you just copy all this data, yeah, from SWAT cup. Yeah, from SWAT cup, because that text in the output folder became the input for your SWAT cup. Okay, so all the modifications would be done in this. So just select output.std from here. The graphical output which I have shown, you will get the text output in these forms. For the complete 12 months, whatever the precipitation is there, surface runoff, lateral flow, groundwater recharge, everything you will get. And the summary also you will get at the end of this file, the basin average values. Yeah, these are the average annual basin values, whatever precipitations you are getting, whatever surface runoff is generating, tile flow, groundwater recharge, everything you will get. So like that you can generate the statistics. Or if you want to interested in your output.reach file, then just go to that RCH file. Yeah, this is related to your discharge related file. So whatever flow is incoming to your any reach, it will shows. Whatever flow is going out, it will shows it. So SWAT cup also use this column for your calibration part. This is the column number 7. So those who have worked in SWAT cup, they know we have to mention the column number, from which column number we have, means comparing our observed data. So observed data will be compared with this column number 7. So you can count column 1, column 2, column 3, column 4, column 5, column 6, column 7. Column 7 is your flow out, that is discharge. So with this we have to compare, and then it computes the R square, NSEP, YS values and all these things. Okay. So this is all about your SWAT. Or those who are working in sediment, so this is also your losses is there, sediment in tons, sediment out in tons. Concentration is also there. They can compare the sedimentation concentrations also. So like that, this is all about SWAT and all these things. So I'll share that steps PPT also. You can practice, or if you have any doubt, you can ask. So I think we'll stop here. ठीक है सर, आप कर दीजिए स्टॉप. भैया स्टॉप कर दीजिए. चलिए, धन्यवाद बहुत बहुत. इसमें एक ऑप्शन जो आपके विजिबल नहीं हो रहा था, वो मैं आपको बता देता हूँ इसमें. दैट इज़ योर विजुअलाइज. दैट इज़ द एडवांटेज.
you.